Part 2, Spring Boot Framework, Databases and Reactive WebFlux.
Welcome back to the Ultimate Production Incident Masterclass for modern Java application support engineers. In this second installment, we move from the core JVM runtime into the enterprise application framework, data persistence, and distributed communications. If you missed Part 1, where we conquered the first 51 incidents across JVM memory, thread deadlocks, and CPU starvation, be sure to check the link in the description below before continuing. Here are the 4 categories of 49 advanced production incidents we will solve in this Part 2 video. Category 4. Spring Boot Framework Runtime, Dependency Injection and Security Incidents 52 to 63. Category 5. Database Connection Pools, Slow SQL, Deadlocks, ORM, and Caching Incidents 64 to 79. Category 6. REST APIs, Microservice Routing, Time Zones, and Serialization Incidents 80 to 94. Category 7. Reactive Programming, Spring WebFlux and Netty Event Loops Incidents 95 to 100. Let's dive into Category 4.
Category 4, Spring Boot and Framework Runtime.
Spring Boot and Framework Runtime Incidents govern how dependency injection, profile configuration, health indicators, embedded servlet containers, and security filters behave across production environments. This category deep dives into resolving circular bean dependencies, profile property mismatches, false positive actuator health probe failures, duplicate scheduled job executions in scaled clusters, refresh scope proxy instabilities, multipart upload limits, and Spring Boot version upgrade migration challenges. Mastering these incidents ensures a stable, fully compliant Spring application runtime.
Category 4, Spring Boot and Framework Runtime 52 to 63.
Here are the 12 Spring Boot and Framework runtime incidents we will solve in this category. Incident 52. Circular dependency breaks Spring context initialization on startup. Incident 53. Wrong Spring profile loaded causing database connection mismatches. Incident 54. Actuator health endpoint reports down due to non-critical component failure. Incident 55. Duplicate scheduled jobs execute simultaneously across scaled pod replicas. Incident 56. At refresh scope, dynamic configuration update causes bean state instability. Incident 57. Tomcat thread pool exhaustion causes HTTP 503 service rejection. Incident 58. Multipart file upload failure caused by size limits or temp directory errors. Incident 59. Spring security blocks legitimate API traffic post deployment. Incident 60. Property resolution mismatch across Spring profiles and config maps. Incident 61. Dependency injection failures caused by bean ambiguity or missing qualifiers. Incident 62. Bean initialization order problems cause unhandled startup exceptions. Incident 63. Spring Boot version upgrade incompatibility breaks runtime configuration. Total 12 Spring Boot Framework incidents. Let us dive into Incident 52.
Production Incident 52. On deployment, a Spring Boot microservice fails to boot, throwing bean currently in creation exception. Requested bean is currently in creation. Is there an unresolvable circular reference between user service and notification service? As the on-call Java application support engineer, how do you resolve this circular dependency startup failure?
Answer. When a Spring Boot application fails context initialization due to a circular bean dependency, my priority is to inspect constructor injection cycles, apply lazy proxy resolution for immediate restoration, and refactor shared domain logic using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application startup logs using kubectl logs to confirm bean currently in creation exception. 2. Identify the 2 conflicting Spring beans creating the circular dependency graph cycle. 3. Verify whether context initialization failure impacts all pod replicas or specific profile configurations. Phase 2. Investigation and evidence gathering. 1. Review constructor injection signatures in user service and notification service for mutual dependencies. 2. Check recent Git commit diffs to identify recent auto-wiring additions or Spring Boot version upgrades. 3. Verify whether circular reference blocking is enforced via Spring Boot configuration spring.main. Allow circular references. Phase 3. Root cause analysis. 1. Evidence collected. Startup logs showed user service constructor requiring notification service, while notification service constructor required user service. 2. Primary root cause. Constructor circular dependency. Both services required each other during constructor instantiation, causing Spring S-Bean factory dependency graph resolution to fail dependency graph resolution during context initialization. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Add at lazy annotation to one of the constructor parameters, for example, at lazy notification service to allow proxy bean creation and restore immediate context startup. 2. Permanent resolution. Refactor shared domain logic into a separate dedicated service or decouple communication using Spring application events. 3. Validation. Confirm pods show 1 out of 1 ready. Spring context initializes in under 15 seconds and API workflows succeed. Phase 5. Recurrence prevention. 1. Enforce Spring Boot default circular reference blocking spring.main. Allow circular references equals false across all environments. 2. Run Arch unit static analysis tests in CI and CD pipelines to detect cyclic component dependencies pre-build. 3. Standardize setter injection or event-driven architecture guidelines across microservice repositories. Pro tip interview insight. Circular dependencies indicate a flaw in component design, while applying at lazy on a constructor parameter provides an immediate workaround by injecting a proxy. The permanent solution is refactoring shared logic into a separate service, or using Spring event listeners to decouple the beans.
Follow-up 1 expected. A logical continuation of the incident. How does applying at lazy on a constructor parameter resolve a Spring circular dependency at runtime?
Answer. Annotating a constructor parameter with at lazy instructs Spring S-Bean factory to inject a dynamic CGLIB proxy instead of instantiating the real bean immediately. The proxy defers actual bean creation until its methods are first invoked at runtime, breaking the initialization cycle.
Follow-up 2 deeper. Experience tester. Why did Spring Boot 2.6 change the default behavior to disable circular references spring.main. Allow circular references equals false?
Answer. Circular references hide architectural flaws, complicate bean lifecycle management, and increase risk of runtime null pointer exceptions if proxies are accessed before underlying target beans are fully initialized. Disabling them forces developers to design clean, acyclic component graphs on startup.
Follow-up 3 curveball. How do Spring application events and at event listener decouple circular dependencies between domain services?
Answer. Instead of user service invoking notification service directly, user service publishes a domain event application event publisher.publish event with new user created event. Notification service listens for the event asynchronously using at event listener, eliminating compile time and runtime bean dependencies.
Production incident 53. Following a production release, a Spring Boot microservice boots successfully, but customer transactions fail immediately with connection refused errors. Investigation reveals the application loaded application dev.yml in prod instead of application prod.yml, connecting to the dev database. As the on-call Java application support engineer, how do you resolve this profile mismatch?
Answer. When a production application boots under the wrong Spring profile, my priority is to inspect environment variable overrides, profile precedents, and deployment config maps, restoring the production profile using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify active Spring profiles in application startup, logs the following one profile is active. Dev. 2. Check database connection, logs via kubectl logs to confirm connection attempts to dev host names. 3. Confirm whether the profile mismatch affects all production pod replicas or specific availability zones. Phase 2. Investigation and evidence gathering. 1. Inspect live container environment variables using kubectl exec pod name --env to check spring_profiles_active. 2. Review Kubernetes deployment manifests and helm values.yaml for unupdated profile environment variables. 3. Check Java system properties --dspring.profiles.active passed in container startup arguments. Phase 3. Root cause analysis. 1. Evidence collected. Kubectl exec --env showed spring_profiles_active equals dev set inside the production pod container. 2. Primary root cause. Profile precedence override. A helm values file, refactoring accidentally hard-coded spring_profiles_active equals dev in the production deployment manifest, overriding default profile settings. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Update spring_profiles_active equals prod in the production Kubernetes deployment manifest via Helm or GitOps and perform a rolling restart. 2. Permanent resolution. Standardize Helm templates to inject environment-specific profiles dynamically based on deployment environment target variables. 3. Validation. Confirm startup logs show the following one profile is active. Prod, verify production database connection and validate transaction health. Phase 5. Recurrence prevention. 1. Implement Spring Boot startup validation custom environment post-processor that fails context startup if prod profile is absent in production clusters. 2. Add automated deployment manifest linter assertions in CI and CD pipelines to block dev profile strings in production release manifests. 3. Audit GitOps release repositories to ensure profile configurations match target deployment environments. Pro tip interview insight. Always verify the active profile line in the Spring Boot startup banner. Environment variables like spring_profiles_active override application.yml defaults. Configure a custom environment post-processor to fail context startup fast if prod profile is not active in production Kubernetes clusters.
Follow up when expected. A logical continuation of the incident. What is the precedence order when setting Spring profiles via spring.profiles.active versus spring.profiles.include versus environment variables?
Answer. OS environment variables, spring_profiles_active and Java system properties -dspring.profiles.active take precedence over profile configurations in application.yml. Spring.profiles.include unconditionally includes secondary subprofiles regardless of the primary active profile.
Follow up deeper. Experienced tester. How do you implement a Spring environment post-processor to fail application startup fast if the prod profile is missing in production?
Answer. Implement Spring S environment post-processor interface. In post-process environment, inspect environment.getActive profiles. If an environment check indicates production execution, for example, checking a Kubernetes cluster ID, but prod is absent, throw a fatal illegal state exception to block container startup immediately.
Follow up 3 curveball. What if both application-prod.yml and a Kubernetes config map define the same property spring.datasource.url? Which value wins?
Answer. If the config map is injected as an OS environment variable spring_datasource_URL, the environment variable wins over application-prod.yml. Spring Boot S property resolution hierarchy places OS environment variables higher than profile-specific YAML configuration files.
Production Incident 54. A Spring Boot microservice is flagged as down by Kubernetes readiness probes, removing pods from the API gateway pool. Application logs show HTTP, APIs, and primary database processing are healthy, but actuator s/actuator/health endpoint returns HTTP 503 down due to an auxiliary disk space check. As the on-call Java application support engineer, how do you resolve this probe outage?
Answer. When a false positive secondary health indicator marks a healthy microservice as down, my priority is to inspect health indicator details, isolate readiness probes, and disable non-critical health checks using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Kubernetes readiness probe failure logs via kubectl. Describe pod confirming HTTP 503 from /actuator/health. 2. Execute kubectl exec running curl/actuator/health to view the detailed JSON status breakdown. 3. Verify whether primary database and core HTTP transaction processing remain operational. Phase 2. Investigation and evidence gathering. 1. Inspect detailed actuator health JSON response for failing components disk space, rabbit DB ping. 2. Review application.yml for property settings, controlling actuator health indicators management.health.star.enabled. 3. Check Kubernetes liveness and readiness probe path configurations in deployment manifests. Phase 3. Root cause analysis. 1. Evidence collected. Actuator health JSON showed status down caused by disk space. Status down free 40 megabytes. 2. Primary root cause. Secondary indicator failure. The default composite /actuator/health endpoint included a disk space health indicator that failed due to temporary build temp files, causing Kubernetes readiness probes to fail and remove healthy API pods from traffic. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. If disk space is not business critical, temporarily disable the indicator or immediately migrate Kubernetes readiness probes to dedicated readiness endpoints management.health.diskspace. Enabled equals false via config map update, and perform a rolling restart to restore readiness probes. 2. Permanent resolution. Configure dedicated Spring Boot probe groups /actuator/health/readiness and /actuator/health/liveness that include only core dependencies. 3. Validation. Confirm pods show 1 out of 1 ready /actuator/health/readiness returns HTTP 200 OK and API gateway traffic resumes. Phase 5. Recurrence prevention. 1. Configure separate dedicated Kubernetes liveness and readiness probe paths across all microservice Helm charts. 2. Exclude non-critical secondary indicators disk space, mail, secondary queues from blocking readiness probes. 3. Implement automated pre-deployment staging validation of actuator health group endpoints. Pro tip interview insight. Never point Kubernetes readiness probes to the default composite /actuator/health endpoint. If secondary health indicators like disk space or secondary queues are included, use Spring Boot as dedicated probe groups /actuator/health/readiness and /actuator/health/liveness to isolate core service health from non-critical auxiliary checks.
Follow up when expected. A logical continuation of the incident. How do Spring Boot 2.3 plus health groups /actuator/health/liveness and /actuator/health/readiness isolate Kubernetes probes?
Answer. Spring Boot 2.3 Plus introduced health groups. /actuator/health/liveness includes only internal JVM state indicators liveness state. /actuator/health/readiness includes only critical traffic readiness indicators readiness state and primary DB. Non-critical secondary health indicators are excluded, preventing false positive probe failures.
Follow up 2 deeper. Experience tester. Why should management.endpoint.health. Show details be set to never or authorized only in production?
Answer. Exposing detailed health JSON in production reveals sensitive internal infrastructure details, database URLs, disk paths, internal host names, and component versions to unauthenticated callers, creating security reconnaissance vulnerabilities.
Follow up 3 curveball. What if a custom health indicator implementation makes a blocking synchronous network call to an external database, and that call hangs indefinitely during a readiness probe check?
Answer. A hanging health indicator blocks the actuator health check thread, causing Kubernetes readiness probes to time out and remove the pod from traffic. To prevent this, custom health indicators must enforce strict timeouts on network health checks or execute checks asynchronously.
Production Incident 55. After scaling a background microservice from 1 to 5 pod replicas, customer accounts receive 5 duplicate email notifications and duplicate payment charges every hour. Investigation reveals Spring at scheduled tasks execute simultaneously on all 5 pod replicas. As the on-call Java application support engineer, how do you resolve this duplicate execution outage?
Answer: when scaled pod replicas execute duplicate scheduled jobs, my priority is to scale down replicas immediately to halt duplicate processing, implement shed lock distributed locking, and restore single pod execution using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application logs across all 5 pod replicas using kubectl logs to confirm duplicate at scheduled executions. 2. Check database audit logs to quantify the extent of duplicate customer charges and notifications. 3. Immediately scale pod replicas down to 1 kubectl scaled deployment -- replicas equals 1 to stop ongoing duplicate processing. Phase 2. Investigation and evidence gathering. 1. Review Spring configuration classes for enable scheduling without shed lock or Quartz distributed locking. 2. Check database or Redis cluster for missing distributed lock tables shed lock. 3. Inspect Git commit history to verify if the service was recently scaled horizontally without distributed locking. Phase 3. Root cause analysis. 1. Evidence collected. Application logs showed all 5 pod replicas executing daily billing job process at 0 UTC. 2. Primary root cause. Missing distributed lock. The at-scheduled tasks relied on Spring's local in-memory scheduler without distributed locking shed lock, causing every scaled pod replica in the deployment to execute the job independently. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Keep deployment scaled to 1 replica while deploying a hotfix adding shed lock at scheduler lock backed by a shared database lock table, then rescale to 5 replicas. 2. Permanent resolution. Configure shed lock at scheduler lock with name equals billing job, lock at most for equals 30M, lock at least for equals 1M on all scheduled methods. 3. Validation. Confirm logs show only 1 pod acquiring the lock while 4 pods skip execution and verify 0 duplicate transactions. Phase 5. Recurrence prevention. 1. Mandate shed lock at scheduler lock annotations on all at scheduled methods across all microservices. 2. Add CI and CD linter rules blocking at scheduled methods lacking at scheduler lock annotations. 3. Implement automated multi-pod staging integration tests, verifying single-pod scheduled job execution. Pro tip interview insight. Spring's default at scheduled annotation executes independently inside every JVM instance where it runs. In a horizontally scaled multi-pod Kubernetes deployment, always annotate scheduled tasks with shed lock at scheduler lock, backed by a shared DB or Redis lock, to guarantee single pod execution.
Follow up when expected. A logical continuation of the incident. How does shed lock at scheduler lock guarantee that only 1 pod replica executes a at scheduled task in a multi-pod cluster?
Answer: before executing a at scheduler lock annotated task, shed lock attempts to insert or update an exclusive row in a shared database or Redis lock table. The pod that successfully acquires the lock executes the task. All other pod replicas fail to acquire the lock and skip execution during that interval.
Follow up 2 deeper. Experienced tester. What is the difference between lock at most for and lock at least for in shed lock, and why are both necessary?
Answer: lock at most for specifies the maximum duration a lock is held if the executing pod crashes, ensuring stale locks expire. Lock at least for specifies the minimum duration a lock must be held, preventing duplicate executions across pods if task execution time is shorter than clock drift variations between nodes.
Follow up 3 curveball. What if a shed lock protected scheduled job requires 45 minutes to execute, but lock at most for is configured to 30 minutes? What goes wrong?
Answer: if task execution exceeds lock at most 4, the database lock expires while the first pod is still running. A second pod replica acquires the newly released lock, triggering concurrent duplicate processing. Lock at most 4 must always be configured slightly longer than the maximum expected execution time.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 56. Support engineers execute a live configuration refresh hitting /actuator/refresh to update a feature property without restarting pods. Immediately, active customer transactions fail with bean creation exception, stateful bean fields reset to null, and thread contention spikes. As the on-call Java application support engineer, how do you resolve this at refresh scope instability?
Answer: when a live configuration refresh destroys stateful bean proxies causing transaction crashes, my priority is to restart pods cleanly, remove at refresh scope from stateful components, and enforce immutable property binding using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Correlate APM error spikes in Grafana with the exact timestamp of the /actuator/refresh endpoint trigger. 2. Check application logs using kubectl logs to capture bean creation exception or null pointer exceptions. 3. Confirm whether transaction failures affect all pod replicas or specific instances, receiving the refresh call. Phase 2. Investigation and evidence gathering. 1. Review stack traces for bean creation exception inside at refresh scope annotated beans. 2. Inspect source code for stateful fields such as in-memory caches, lists, or connection state stored inside at refresh scope beans. 3. Verify whether concurrent HTTP worker threads were actively executing bean methods when the proxy was destroyed. Phase 3. Root cause analysis. 1. Evidence collected. Logs showed bean creation exception and null pointer exception inside payment routing service immediately after calling /actuator/refresh. 2. Primary root cause. Mutable state in refresh scope bean. Payment routing service was annotated with at refresh scope, but maintained an internal in-memory routing map initialized at boot. The live refresh destroyed and recreated the underlying target bean behind the at refresh scope proxy, wiping the internal map state and causing active request threads to crash. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to reinitialize all Spring beans cleanly from environment configuration and restore customer traffic. 2. Permanent resolution. Remove at refresh scope from stateful beans, moving dynamic property bindings into dedicated, stateless at configuration properties beans. 3. Validation. Execute /actuator/refresh in staging under load, verify 0 bean creation exception errors, and confirm transaction health. Phase 5. Recurrence prevention. 1. Prohibit at refresh scope annotations on stateful beans, restricting usage exclusively to stateless helper beans. 2. Adopt immutable at configuration properties with dynamic property binding instead of dynamic bean proxy recreation. 3. Mandate staging load testing validation before triggering live /actuator/refresh endpoints in production. Pro tip interview insight. Spring Cloud at refresh scope retains the proxy, but destroys and recreates the underlying target bean when /actuator/refresh is called. Never put at refresh scope on stateful beans holding caches or connection state, as recreating the target bean wipes its internal state and can trigger race conditions under high concurrency.
Follow up when expected. A logical continuation of the incident. How does Spring Cloud at refresh scope dynamically update bean properties at runtime without restarting the JVM?
Answer: at refresh scope creates a lazy CGLIB proxy wrapper around the target bean. When /actuator/refresh is invoked, Spring Cloud clears the target bean instance from the refresh scope context. The next time a method is called on the proxy, Spring lazily re-instantiates the bean with updated property values.
Follow up 2 deeper. Experienced tester. Why can calling /actuator/refresh trigger thread contention and latency spikes in high-throughput microservices?
Answer: when /actuator/refresh destroys the proxy target instance, all concurrent worker threads calling that bean simultaneously block on a lock, while Spring recreates and rewires the new bean instance, creating a brief synchronization, bottleneck under high traffic.
Follow-up 3 curveball. How do immutable at configuration properties beans combined with Spring Cloud Bus eliminate the dangers of at refresh scope?
Answer: Spring Cloud Bus uses a lightweight message broker, RabbitMQ or Kafka, to broadcast property change events across all microservice instances. Combined with immutable at configuration properties records, properties update threads safely via atomic reference swaps without destroying bean proxy instances or losing internal state.
Production Incident 57. A Spring Boot web microservice experiences severe latency spikes and HTTP 503 errors during a marketing campaign. APM dashboards show embedded Tomcat worker threads reaching 100% capacity, 200 out of 200 threads occupied, while CPU usage remains low at 15%. As the on-call Java application support engineer, how do you resolve this Tomcat thread exhaustion?
Answer: when embedded Tomcat thread pools exhaust while CPU usage remains low, my priority is to inspect thread states, isolate blocking I/O calls, apply bulkhead thread limits, and restore request processing using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM thread pool metrics to confirm Tomcat busy thread counts equal maximum capacity, busy_threads equals 200. 2. Check container CPU utilization in Grafana to verify CPU usage is low 15%, ruling out CPU-bound execution loops. 3. Verify the rate of HTTP 503 service unavailable and task rejected exception errors across web pods. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using jcmd1 thread.print. 2. Analyze stack traces for HTTP Neo 8080 exec star worker threads to determine why 200 threads are stuck in waiting or timed_waiting state. 3. Check APM dependency maps to measure response times of downstream database queries and external HTTP REST calls. 4. Review embedded Tomcat configuration in application.yml server.tomcat.threads.max. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump revealed 185 Tomcat exec threads blocked in socket input stream.socket read. 0. Executing synchronous HTTP REST calls to an untimed external recommendation engine API. 2. Primary root cause. Blocking I/O starvation. A slow external recommendation API experienced latency spikes, causing 185 Tomcat worker threads to block waiting for socket reads and exhausting the 200 thread pool. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Apply socket read timeouts on the recommendation client. Temporarily increase Tomcat max threads server.tomcat.threads.max equals 400 and perform a rolling restart. 2. Permanent resolution. Apply resilience 4J bulkhead thread isolation on the recommendation API client and refactor calls to use Spring Web Client. 3. Validation. Confirm Tomcat busy threads drop to baseline 20 threads. HTTP 503 errors clear and API latencies normalize. Phase 5. Recurrence prevention. 1. Enforce resilience 4J bulkhead thread isolation across all external HTTP integrations. 2. Configure Prometheus alerts for Tomcat busy thread utilization exceeding 80% of max pool size. 3. Mandate explicit socket connect and read timeouts on all HTTP client beans. Pro tip interview insight. Tomcat thread pool exhaustion with low CPU usage always indicates worker threads blocked on I/O database or external HTTP calls. Simply increasing server.tomcat.threads.max consumes more memory without solving the root cause. Apply socket timeouts and resilience 4J bulkhead thread isolation on external calls.
Follow-up when expected. A logical continuation of the incident. How do you determine whether thread pool exhaustion is caused by high traffic volume versus downstream blocking I/O?
Answer: check container CPU utilization alongside busy thread counts. High busy threads with high CPU usage indicates real traffic load or CPU-bound code. High busy threads with low CPU usage, for example 15%, indicates worker threads blocked on I/O database locks or slow external API socket reads.
Follow up 2 deeper. Experience tester. How does configuring server.tomcat.accept count and server.tomcat.max connections affect TCP connection queuing during thread pool exhaustion?
Answer: max connections is the maximum number of TCP connections Tomcat accepts. Accept count is the OSTCP listen queue length when all worker threads are busy. When accept count fills up, the OS kernel rejects incoming TCP connections, with connection refused.
Follow up 3 curveball. What happens if a Spring WebFlux application running on Netty experiences event loop thread exhaustion? How does it differ from Tomcat thread exhaustion?
Answer: Netty uses a tiny pool of event loop threads equal to CPU cores, for example 4 threads. If a developer executes a blocking database or I/O call directly on a Netty event loop, one blocked thread freezes 25% of the entire application capacity, degrading performance much faster than Tomcat.
Production Incident 58. An invoice processing microservice starts rejecting document uploads with max upload size, exceeded exception, and multipart exception. Logs reveal file uploads fail with java.io.io exception. The temporary upload location is not valid. As the on-call Java application support engineer, how do you resolve this multipart upload failure?
Answer: when multipart file uploads fail due to temp location deletion or size breaches, my priority is to inspect upload directory locations, adjust file size bounds, and configure persistent temporary storage using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application error logs using kubectl logs to confirm max upload size exceeded exception or multipart exception. 2. Check container/temp disk space and file system permissions to verify temporary directory availability. 3. Confirm whether upload failures impact all document processing workflows or specific large file types. Phase 2. Investigation and evidence gathering. 1. Review Spring Boot multipart property settings in application.yml spring.servlet.multipart.max file size and spring.servlet.multipart.max request size. 2. Check whether the temporary upload directory was removed by host OS cleanup utilities VM deployments or by ephemeral container file system lifecycle events Kubernetes containers. 3. Test file upload endpoints using curl-f from worker nodes to isolate API gateway payload caps. Phase 3. Root cause analysis. 1. Evidence collected. Application logs show java.io.io exception. The temporary upload location /temp/tomcat.8080.1234/work is not valid. 2. Primary root cause. Ephemeral temp location deletion. A Linux OS background temp cleaner script deleted Tomcat's temporary upload directory while the container was running, causing subsequent multipart uploads to fail. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Configure an explicit temporary directory spring.servlet.multipart.location =/app/temp via config map update and perform a rolling pod restart. 2. Permanent resolution. Create a dedicated /app/temp directory in the base Docker file and increase max file size limits to handle peak invoice documents. 3. Validation. Upload test documents, verify 0% multipart exception errors, and confirm clean file processing. Phase 5. Recurrence prevention. 1. Standardize explicit, non-system temporary upload directories across all base container Docker file templates. 2. Configure Prometheus alerts for container disk space utilization and temporary file cleanup errors. 3. Implement automated CI and CD integration tests, asserting large file upload limits. Pro tip interview insight. Never rely on default OS/temp directories for Spring Boot multipart file uploads. Linux background temp cleaners like tmpfiles.d can delete Tomcat's temporary upload directory while the container is running, causing subsequent file uploads to fail. Always configure an explicit spring.servlet.multipart.location directory.
Follow up when expected. A logical continuation of the incident. What is the precise difference between spring.servlet.multipart.max file size and spring.servlet.multipart.max request size in Spring Boot?
Answer: max file size specifies the maximum allowed size for any single individual file in a multipart upload request. Max request size specifies the total maximum allowed size for the entire HTTP request payload, including all uploaded files plus form parameters combined.
Follow up 2 deeper. Experience tester. How do you stream multipart file uploads directly to AWS S3 or blob storage without buffering the entire file on container disk memory?
Answer: instead of accepting standard multipart file which buffers bytes to disk, configure Spring WebFlux or custom input streams using part or input stream. Stream incoming network chunked byte buffers directly to S3 via the AWS SDK Multipart Upload API, keeping container disk and heap memory usage minimal.
Follow up 3 curveball. What if a Spring Boot file upload request fails before reaching application controllers because an upstream API gateway or ingress controller rejected the body size limit?
Answer: this manifests as an HTTP 413 payload too large error returned directly by Nginx ingress or API gateway before reaching Spring Boot. To fix, update ingress annotations nginx.ingress.kubernetes.io/proxy body size. 50 megabytes and gateway request size limits to match application multipart settings.
Production Incident 59. Following a production deployment, legitimate API requests from mobile and web applications are blocked with HTTP 403 forbidden and HTTP 401 unauthorized errors across all endpoints. As the on-call Java application support engineer, how do you resolve this Spring security traffic blocking outage?
Answer: when a security configuration deployment blocks legitimate production users, my priority is to inspect security filter chain ordering, verify CORS pre-flight options mappings, and fix token evaluation rules using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check Grafana APM HTTP response metrics to confirm a sharp spike in HTTP 401 unauthorized and 403 forbidden responses. 2. Verify whether security blocks impact all API endpoints or specific authenticated routes. 3. Check Splunk or ELK security logs to capture specific access, denied exception, or insufficient authentication exception, stack traces. Phase 2. Investigation and evidence gathering. 1. Review security filter chain authorization rules, request matchers and filter ordering. 2. Inspect CORS cross-origin resource sharing configuration for missing allowed origins or headers. 3. Test browser pre-flight options, request using curl-x options to check if CORS requests fail prior to JWT authentication. 4. Verify whether custom security filters were placed ahead of standard authentication filters in the filter chain. Phase 3. Root cause analysis. 1. Evidence collected. Browser pre-flight options, requests returned HTTP 403 forbidden without CORS headers. 2. Primary root cause. Security filter chain order misconfiguration. A security refactoring placed JWT authentication filter ahead of CORS filter, causing unauthenticated browser options pre-flight requests to be rejected before CORS headers were evaluated. Phase 4. Resolution and service restoration. 1. Immediate recovery, reduce MTTR. Reorder security filter chain using http.add filter before with CORS filter. JWT authentication filter.class or explicitly permit options requests, then perform a rolling restart. 2. Permanent resolution. Standardized security filter chain configuration templates across all microservices, ensuring CORS filter executes prior to authentication filters. 3. Validation. Confirm browser pre-flight options requests return HTTP 200 OK, 403 forbidden spike cease, and user login succeeds. Phase 5. Recurrence prevention. 1. Implement automated Spring security integration tests using mock MVC, explicitly validating CORS pre-flight options requests. 2. Enforce standardized security filter chain archetype templates across all microservice repositories. 3. Conduct pre-release staging security audits, verifying JWT and CORS filter evaluations. Pro tip interview insight. In Spring Security, filter order is critical. Pre-flight HTTP options, requests issued by web browsers, must be handled by CORS filter before JWT or session authentication filters execute. If your JWT filter runs first, pre-flight options requests will fail with HTTP 403 forbidden.
Follow-up when expected. A logical continuation of the incident. How do pre-flight HTTP options requests work in CORS, and why must Spring security permit options requests unauthenticated?
Answer. Browsers send automatic pre-flight HTTP options requests before cross-origin requests to check server permissions. These pre-flight requests do not carry authentication credentials like JWT headers. If Spring Security blocks unauthenticated options requests, the browser blocks the subsequent actual API call.
Follow-up 2 deeper. Experienced tester. What is the difference between security filter chain bean configuration in Spring Security 5 versus Spring Security 6?
Answer. Spring Security 5 relied on extending Web Security Configurer adapter. Spring Security 6 completely removed Web Security Configurer adapter, requiring explicit component-based security filter chain beans using Lambda DSL configuration, for example. HTTP.CORS with customizer. With defaults.
Follow-up 3 curveball. What if a JWT authentication filter succeeds in parsing the token, but Spring Security still returns HTTP 403 forbidden because granted authorities' role prefixes do not match?
Answer. By default, Spring Security has role with user expects the authority string to carry the role underscore prefix role underscore user. If the JWT token claims list roles as user without the prefix, access is denied. To fix, configure a custom JWT authentication, converter to strip, or prepend the role underscore prefix consistently.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 60. A Spring Boot service deployed to production connects to the wrong database URL and uses incorrect timeout values. Investigation reveals at value placeholders and at configuration properties resolved properties from application.yml instead of production Kubernetes config maps. As the on-call Java application support engineer, how do you resolve this property mismatch?
Answer. When production applications resolve fallback properties instead of Kubernetes config map overrides, my priority is to inspect environment variable key naming, verify relaxed binding rules, and enforce property validation using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect active property values at runtime using actuator/actuator/env or database connection startup logs. 2. Verify whether property resolution mismatches impact all production pods or specific microservice instances. 3. Check database logs to confirm whether the service is attempting connections to fallback URL addresses. Phase 2. Investigation and evidence gathering. 1. Inspect configured environment variables inside the container using kubectl exec pod name --env. 2. Compare environment variable key syntax in the Kubernetes config map against Spring Boot relaxed binding rules. 3. Review at configuration properties prefix definitions and field names in Java source code. Phase 3. Root cause analysis. 1. Evidence collected. Actuator/actuator/env showed Spring_datasource_max-active present in environment, but Spring.datasource.hikari.maximum pool size resolved to default value 10. 2. Primary root cause. Property key syntax mismatch. The Kubernetes config map used dashes instead of _spring _data source _max-active, using an environment variable name that Spring Boot could not correctly bind to the intended property according to its environment variable naming convention, and causing Spring to silently fall back to application.yml defaults. Phase 4. Resolution and Service Restoration. 1. Immediate recovery. Reduce MTTR. Correct environment variable key syntax in the production config map Spring _data source _max_active via Helm or GitOps and perform a rolling pod restart. 2. Permanent resolution. Standardize property key definitions across Helm chart templates using uppercase _ syntax. 3. Validation. Confirm /actuator/env shows properties resolving from environment variables and verify database connection pool limits. Phase 5. Recurrence prevention. 1. Enforce mandatory Jakarta validation at validated and at not null on all at configuration properties beans, so unresolved properties fail startup fast. 2. Implement automated pre-deployment schema validation in CI and CD pipelines, comparing config map keys against Java property beans. 3. Audit GitOps templates to ensure environment variable key alignment across all environments. Pro tip: interview insight. Environment variables in Kubernetes config maps must follow Spring Boot's relaxed binding rules. Use uppercase letters and replace dots and dashes with underscores, for example Spring _data source _max_active for spring.datasource.maxactive. Misspelled environment variables cause Spring Boot to silently fall back to application.yml defaults.
Follow up when expected. A logical continuation of the incident. How does Spring Boot's relaxed binding rule convert environment variables like Spring _Kafka _consumer _auto _offset reset to YAML properties?
Answer: Spring Boot converts uppercase environment variable names to lowercase dot notation properties. Underscores are converted to dots or dashes. Spring _Kafka _consumer _auto _offset reset maps directly to spring.kafka.consumer.auto offset reset in YAML configuration.
Follow up 2 deeper. Experience tester. Why should critical infrastructure properties always use Jakarta validation at not null on at configuration properties beans instead of relying on default fallback values?
Answer: default fallback values mask missing production configuration. If a production config map key is misspelled or omitted, Spring Boot silently uses the fallback default, connecting to unintended hosts. Adding at validated and at not null forces the JVM context to crash instantly on startup with a clear validation report.
Follow up 3 curveball. What if a property value defined in an environment variable is wrapped in single quotes inside the Kubernetes config map, causing Spring Boot to treat numeric or Boolean values as literal raw strings?
Answer: Spring Boot's property binding engine attempts automatic type conversion. However, literal quotes inside environment variable strings, for example 5000 cause string to integer conversion failures. To fix, remove outer quotes from config map values, or configure explicit custom converter beans in Spring's conversion service.
Production Incident 61. A production deployment fails during Spring context initialization with no unique bean definition exception, no qualifying bean of type com.example.payment service available. Expected single matching bean but found 2. Credit card payment service, PayPal payment service. As the on-call Java application support engineer, how do you resolve this dependency injection failure?
Answer: when a Spring Boot application fails startup due to ambiguous bean definitions, my priority is to inspect bean factory resolution rules, specify bean qualifiers or primary candidates, and restore context boot using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application startup logs using kubectl logs to confirm no unique bean definition exception. 2. Identify the target interface type and the multiple matching bean implementation names listed in the exception. 3. Confirm whether the startup failure affects all microservice replicas or specific profile deployments. Phase 2. Investigation and evidence gathering. 1. Review Spring component scanning rules and at bean method definitions for payment service implementations. 2. Check auto wiring sites for missing at qualifier or at primary annotations. 3. Inspect recent Git commits to identify newly introduced bean classes implementing shared interfaces. Phase 3. Root cause analysis. 1. Evidence collected. Startup logs showed no unique bean definition exception for payment service, with candidates credit card payment service and PayPal payment service. 2. Primary root cause. Ambiguous bean injection. A new developer added PayPal payment service implementing payment service, without adding at qualifier at injection sites or marking one implementation as at primary, causing Spring Bean Factory to fail on startup. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Add at primary annotation to credit card payment service or specify at qualifier with credit card payment service at auto wiring injection sites and perform an emergency rolling deployment. 2. Permanent resolution. Enforce explicit at qualifier annotations or conditional bean loading at conditional on property across all multi-implementation interfaces. 3. Validation. Confirm pods show 1 out of 1 ready Spring context initializes cleanly and payment workflows succeed. Phase 5. Recurrence prevention. 1. Implement automated Spring integration tests at Spring Boot test in CI and CD pipelines to validate context initialization across all profiles before production release. 2. Enforce architecture linter rules requiring explicit qualifiers on multi-implementation auto-wired interfaces. 3. Standardize conditional bean registration models across shared framework libraries. Pro tip interview insight. When multiple Spring beans implement the same interface, Spring cannot determine which bean to auto-wire without explicit instructions. Always use at qualifier with bean name, or mark the default implementation with at primary, or use at conditional on property to selectively instantiate beans based on active configuration.
Follow up when expected. A logical continuation of the incident. What is the precise architectural difference between at qualifier and at primary in Spring dependency injection?
Answer. At primary sets a global default bean implementation whenever an unqualified injection point requests that interface type. At qualifier with bean name explicitly targets a specific named bean at a local injection site, overriding any at primary default.
Follow up 2 deeper. Experienced tester. How does at conditional on property allow Spring Boot to selectively load bean implementations based on configuration properties?
Answer. At conditional on property with name equals payment.provider. Having value equals PayPal instructs Spring Bean Factory to instantiate the annotated bean only if the specified property exists and matches the expected value, preventing bean ambiguity at startup.
Follow up 3 curveball. What if a Spring context fails to boot with no such bean definition exception because a bean class is located outside Spring Boot's default at Spring Boot application component scan package?
Answer. Spring Boot scans sub-packages beneath the main class containing at Spring Boot application by default. If a bean resides in an external package, such as com.shared.library, Spring ignores it. To fix, explicitly add a component scan with base packages equals com.example, com.shared, or import the bean via a configuration class.
Production Incident 62. A Spring Boot microservice crashes on startup during a release rollout with cannot load JDBC driver exception or table not found exception. Investigation reveals a Spring bean annotated with at post construct attempted to execute database queries before Flyway database migrations had completed. As the on-call Java application support engineer, how do you resolve this initialization order failure?
Answer. When a Spring bean executes startup database operations before migration beans complete, my priority is to enforce explicit bean dependency ordering, shift warmups to application-ready event listeners, and restore startup health using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application startup, stack traces via kubectl logs for database exceptions occurring inside at post-construct methods. 2. Check whether database migrations Flyway or Liquibase were interrupted or skipped prior to application bean creation. 3. Verify whether context initialization failure impacts all deployment replicas. Phase 2. Investigation and evidence gathering. 1. Inspect the failing bean class for at-post construct or initializing bean. After properties set methods performing database I/O. 2. Review Spring Bean initialization graph to check if the bean lacks explicit dependencies on Flyway initializer or entity manager factory. 3. Check whether database migration scripts executed successfully in the Flyway_schema_history table. Phase 3. Root cause analysis. 1. Evidence collected. Startup logs showed table not found exception. Table orders does not exist inside cache warmer. In it annotated with at post construct. 2. Primary root cause. Bean initialization order mismatch. A custom cache warmer bean executed SQL queries inside its at post construct method. But Spring initialized the cache warmer bean times before times Flyway executed database schema migrations, causing startup queries to fail on missing tables. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Add it depends on with Flyway initializer to the cache warmer bean class and perform an emergency rolling deployment. 2. Permanent resolution. Refactor startup database warmups out of at post construct methods into an application listener of application ready event bean. 3. Validation. Confirm Flyway migrations complete first. Cache warming executes cleanly and pods show 1 out of 1 ready. Phase 5. Recurrence prevention. 1. Prohibit database and network I/O calls inside at post construct methods across all codebase repositories. 2. Standardize startup warmup tasks using Spring application ready event listeners. 3. Add automated integration tests validating context boot order across database migration boundaries. Pro tip interview insight. Spring at post construct methods execute after bean instantiation and dependency injection have completed, but before the application is fully ready to serve requests, which may be before database migrations Flyway or Liquibase or JPA entity manager factories are fully initialized. Move startup data warmups to an application listener of application ready event to guarantee all infrastructure beans and database schemas are ready.
Follow-up 1 expected. A logical continuation of the incident. What is the precise execution order of at post construct, initializing bean. After properties set? An application, runner in a Spring Boot application lifecycle.
Answer. At post, construct executes first immediately after bean construction. Initializing bean. After properties set executes second during bean property wiring. Application runner and command line runner executes last. After the entire Spring application context is fully refreshed, an embedded Tomcat web server is running.
Follow-up 2 deeper. Experience tester. How does the at depends on annotation explicitly force Spring bean factory to initialize specific beans before others?
Answer. At depends on with Flyway initializer. Instructs Spring bean factory that the annotated bean requires Flyway initializer to be fully instantiated and initialized first. Spring guarantees the dependent on bean lifecycle completes before creating the dependent bean, ensuring database schema readiness.
Follow-up 3 curveball. What if an application ready event listener executes a heavy 2-minute database warmup on startup, causing Kubernetes readiness probes to fail and restart the pod in a loop?
Answer. By default, application ready event fires after Spring Boot considers the application ready. However, if readiness probes are configured on /actuator/health and the warmup thread blocks HTTP processing, probes fail. To fix, execute heavy warmups asynchronously on a separate thread pool or adjust probe initial delay seconds.
Production Incident 63. An enterprise microservice is upgraded from Spring Boot 2.7 to Spring Boot 3.2 on Java 17. The application compiles, but crashes on startup with class not found exception, javax.servlet.filter, and database connection failures. As the on-call Java application support engineer, how do you resolve this Spring Boot major upgrade outage?
Answer. When a major Spring Boot 3 upgrade crashes on startup due to Jakarta EE package renames and modified property prefixes, my priority is to update package namespaces, align property keys, and restore application boot using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect startup logs via kubectl logs to confirm java.lang.class not found exception java x/servlet/filter or unbound properties. 2. Confirm whether the upgrade crash impacts all microservice deployment replicas. 3. Review project build commits to verify Spring Boot 2.x to 3.x and Java 17 upgrade changes. Phase 2. Investigation and evidence gathering. 1. Review source code, import statements across servlets, filters, and JPA entities for legacy Java x.star packages. 2. Compare application.yml property key prefixes against Spring Boot 3 migration guides, for example, Spring.Redis renamed to Spring.data.Redis. 3. Inspect security filter chain bean definitions for deprecated Spring Security 5 Web Security Configurer Adapter classes. Phase 3. Root cause analysis. 1. Evidence collected. Startup logs showed class not found exception. javax.servlet.filter and unknown property spring.redis.host. 2. Primary root cause. Spring Boot 3 major upgrade incompatibility. Spring Boot 3 migrated from Java EE Java x.star to Jakarta EE10 Jakarta.star and modified core property prefixes, causing unmigrated imports and properties to fail at runtime. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Update package imports from javax.servlet.star and javax.persistence.star to jakarta.servlet.star and jakarta.persistence.star. Update property prefixes in application.yml and perform an emergency rolling deployment. 2. Permanent resolution. Update all application source code. Package imports javax.star to jakarta.star, JAXB-related dependencies, generated SOAP stubs, and Spring Boot configuration changes required for Jakarta EE compatibility. 3. Validation. Confirm pods show 1 out of 1 ready Spring Boot 3 boots in under 10 seconds and synthetic API workflows succeed. Phase 5. Recurrence prevention. 1. Mandate automated open, rewrite Spring Boot 3 migration recipes in CI and CD pipelines before upgrading major versions. 2. Enforce comprehensive integration test suites in staging prior to approving major framework version upgrades. 3. Standardize property key validation and Jakarta package rules in shared parent POMS. Pro tip interview insight. Spring Boot 3 requires Java 17 plus and migrates entirely from Java EE Java x.star to Jakarta EE10 Jakarta.star. Key property prefixes also changed. For example, Spring.Redis became Spring.data.Redis. Always run open rewrite automated migration recipes before upgrading major Spring Boot versions.
Follow up when expected. A logical continuation of the incident. How do you use open, rewrite automated migration recipes to convert a Spring Boot 2.x codebase to Spring Boot 3.x automatically?
Answer. Add the open rewrite maven plugin org.open rewrite.maven : rewrite maven plugin to pom.xml and execute mvn rewrite : run -d rewrite.recipe artifact coordinates equals org.open rewrite.recipe : rewrite spring : release -d rewrite.active recipes equals org.open rewrite.java.spring.boot 3.upgrade Spring Boot _3_0. Open rewrite automatically refactors Java X imports, updates maven dependencies, and renames modified property keys.
Follow up 2 deeper. Experienced tester. How did Spring Security 6 in Spring Boot 3 replace Web Security Configurer Adapter with a security filter chain bean pattern?
Answer. Spring Security 6 removed Web Security Configurer Adapter. Security configuration is now defined by declaring @bean returning security filter chain. Using lambda DSL syntax, for example, http dot authorize http requests with auth to auth dot any request dot authenticated for type safe, component-based security authorization.
Follow up 3 curveball. What if a third-party vendor library inside a Spring Boot 3 application still references old javax.servlet packages and has no updated Jakarta release available?
Answer: if an unupdated vendor library relies on javax.servlet, use Apache Tomcat S migration tool for Jakarta EE or the Eclipse Transformer plugin in your build pipeline. Transformer rewrites bytecode inside third-party dependency jars at build time, converting JavaX package references to Jakarta without requiring source code modifications.
Category 4 Conclusion.
Mastering Spring Boot framework initialization, property binding, health probe isolation, and security filter order is what protects enterprise Java applications from false positive probe outages, profile configuration leaks, and deployment startup crashes. By enforcing explicit property validation, isolating actuator readiness probe groups, and using Spring Boot 3 migration automation, you build a resilient, fully compliant Spring application runtime.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details: 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 4 Spring Boot and Framework Runtime to Category 5 Database, ORM, Cache and Batch.
While a cleanly initialized Spring Boot framework and healthy container probes guarantee application startup, your microservices cannot process business transactions if database queries hang or connection pools exhaust. Connection leaks, database deadlocks, missing indexes, replication lag, and cache inconsistency can instantly degrade transaction throughput across your entire platform. We now transition from application framework layers to data persistence and caching architecture. Category 5. Database ORM Cache and Batch.
Category 5 Database ORM Cache and Batch.
Database ORM Cache and Batch scenarios govern how transactional persistence, relational query optimization, distributed caching, and bulk batch processing behave under heavy production loads. This category deep dives into resolving HikariCP connection pool exhaustion, unindexed slow SQL queries, database deadlocks, JDBC connection leaks, Hibernate N+1 query storms, master replica replication lag, Redis cache stampedes, and Spring batch failures. Mastering these scenarios ensures a highly scalable, low-latency data access layer.
Category 5 Database ORM Cache and Batch 64 to 79.
Here are the 16 database, cache, and batch processing incidents we will solve in this category. Incident 64. Connection pool exhaustion causes transaction timeout failures. Incident 65. Slow SQL queries degrade application response times under load. Incident 66. Database deadlocks terminate concurrent transactional updates. Incident 67. Missing indexes trigger full table scans and database CPU spikes. Incident 68. JDBC connection leaks deplete connection pools over time. Incident 69. Unexpected rollback exceptions in nested transactional methods. Incident 70. Master replica database replication lag causes stale data reads. Incident 71. Hibernate N+1 query problem drives up database execution latency. Incident 72. Redis connection pool exhaustion crashes caching layers. Incident 73. Cache stampede thundering herd overloads primary database. Incident 74. Cache inconsistency produces stale business data across services. Incident 75. Spring batch job restart failure blocks automated data pipelines. Incident 76. Quartz scheduler duplicate executions trigger duplicate batch runs. Incident 77. Large file processing batch job crashes with out-of-memory error. Incident 78. Optimistic locking failures cause concurrent transaction rejections. Incident 79. Database failover triggers connection storms and pool lockups. Total 16 database, cache, and batch incidents. Let's dive into Incident 64.
Production Incident 64. A high-throughput order checkout service starts rejecting customer transactions with Hikari pool. One connection is not available. Request timed out after 30 seconds. APM dashboards show HikariCP active connections at 100% capacity 30 out of 30 connections occupied. As the on-call Java application support engineer, how do you resolve this connection pool exhaustion?
Answer. when database connection pools exhaust while database CPU remains low, my priority is to inspect connection usage metrics, isolate long-running queries holding pool connections, and configure connection leak detection using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect HikariCP pool metrics in Grafana to confirm active connections equal maximum capacity HikariCP active connections equals 30. 2. Check database server CPU utilization to verify whether the database is overloaded or running normally. 3. Confirm whether transaction timeout failures affect all checkout pods or specific availability zones. Phase 2. Investigation and evidence gathering. 1. Generate a JVM thread dump using jcmd1 thread.print. 2. Analyze stack traces for worker threads stuck in Hikari pool. Get connection waiting for available pool connections. 3. Check database active session tables pg_stat_activity or show process list to locate queries holding connections for over 10 seconds. 4. Review HikariCP configuration in application.yml spring.datasource.hikari.maximum pool size. Phase 3. Root cause analysis. 1. Evidence collected. Database session queries showed 30 active connections executing unindexed full table scan queries averaging 12 seconds per execution. 2. Primary root cause. Long-running slow queries. Unindexed database queries held HikariCP connection instances for over 10 seconds per checkout request, exhausting the 30 connection pool under high concurrent user load. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily increase HikariCP maximum pool size only if the database has available capacity, while immediately terminating or optimizing the long-running queries holding connections. Perform a rolling restart if necessary to restore service. 2. Permanent resolution. Optimize slow database queries by adding required indexes and configuring query execution timeouts. 3. Validation. Confirm HikariCP active connection counts drop to baseline 8 connections. Timeout errors disappear and transaction processing normalizes. Phase 5. Recurrence prevention. 1. Configure leak detection threshold equals 2000 in HikariCP settings to log stack traces of threads holding connections longer than 2 seconds. 2. Enforce mandatory JPA query execution timeouts javax.persistence.query.timeout across all repository beans. 3. Configure Prometheus alerts for sustained HikariCP pool utilization above 80% together with increasing connection acquisition latency to detect impending pool exhaustion before customer impact. Pro tip interview insight. Connection pool exhaustion is usually a symptom of slow SQL queries holding connections too long, not an undersized pool. Always set leak detection threshold equals 2000 in HikariCP to log stack traces of threads holding connections for longer than 2 seconds.
Follow up when expected. A logical continuation of the incident. Why is increasing HikariCP maximum pool size from 30 to 200 usually counterproductive under database load?
Answer. Increasing database connections beyond database CPU core capacity increases disk I/O, OS thread context switching, and lock contention on database servers. A smaller, well-tuned connection pool combined with fast queries achieves significantly higher transaction throughput than a massive connection pool.
Follow up 2 deeper. Experienced tester. How does HikariCP leak detection threshold identify connection leaks without impacting production performance?
Answer. When a thread borrows a connection from HikariCP, a lightweight scheduled task is scheduled for execution after the threshold interval, for example, 2000 milliseconds. If the connection is closed and returned before the timer, the task is canceled. If not returned, the task logs a warning stack trace showing where the connection was borrowed.
Follow up 3 curveball. What if a database connection pool is healthy, but application threads block indefinitely on data source.get connection due to a network partition between Kubernetes and the database host.
Answer: if network packets are dropped silently without TCP/RST or FIN, TCP connection attempts hang. To fix, configure HikariCP connection timeout equals 5005 seconds and validation timeout equals 3003 seconds alongside OSTCP keep alive settings to fail fast rather than hanging threads indefinitely.
Production Incident 65. Following a data growth milestone, a user search endpoint degrades severely. HTTP API response times jump from 50 milliseconds to 12 seconds, triggering connection timeouts in upstream gateways. Investigation reveals a single unindexed SQL query performing full table scans on 20 million rows. As the on-call Java application support engineer, how do you resolve this slow SQL outage?
Answer: when an unindexed SQL query degrades API response times due to full table scans, my priority is to analyze query execution plans, create targeted non-blocking database indexes, and optimize data access using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect a PM database transaction, traces to identify the specific SQL query string exceeding 10 seconds execution time. 2. Check database server CPU metrics in Grafana to verify if full table scans are driving database host CPU saturation. 3. Confirm whether query slowness affects all search operations or specific search parameter combinations. Phase 2. Investigation and evidence gathering. 1. Retrieve active slow queries from Postgres SQL PG_stat_activity or MySQL performance schema. 2. Execute database explain analyze on the slow query to inspect execution plans for sec scan or all table scans. 3. Review database table row counts and index definitions on the user's table. 4. Inspect JPA repository methods and Spring data criteria queries generating the SQL statement. Phase 3. Root cause analysis. 1. Evidence collected. Explain analyze output showed sec scan on user's cost equals 0.00 to 482,910.00 rows equals 20 million taking 11.8 seconds. 2. Primary root cause. Missing functional index. The user search query filtered on lower with email and status without a composite index, forcing the database engine to execute sequential full table scans across 20 million rows on every request. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Execute an online non-blocking index creation. Create index concurrently IDX_users _email status on users lower with email status on the database to restore. Query execution immediately. 2. Permanent resolution. Add the index creation to version-controlled flyway or liquid-based migration so every environment remains schema consistent. 3. Validation. Rerun explain analyze, confirm execution plan switches to index scan, and verify search API response times drop below 5 milliseconds. Phase 5. Recurrence prevention. 1. Implement automated CI and CD query execution plan, linting to detect unindexed where clauses pre-deployment. 2. Configure slow query, logging thresholds log_min_duration_ statement equals 500 milliseconds in database server configurations. 3. Mandate explain plan reviews for all new JPA repository queries prior to production releases. Pro tip interview insight. Never diagnose slow SQL by guessing. Always run explain analyze in Postgres SQL or explain format equals JSON in MySQL to view the actual execution plan. Look for sec scan or all which indicate full table scans and create targeted indexes to convert them into B-tree index scans.
Follow up when expected. A logical continuation of the incident. What is the difference between explain and explain analyze in Postgres SQL query tuning?
Answer. Explain generates an estimated execution plan using database optimizer statistics, without executing the query. Explain Analyze actually executes the query on the database, providing real execution times, actual row counts, and memory usage per planned node.
Follow up 2 deeper. Experience tester. Why does applying a function like lower with email in a SQL where clause invalidates standard B-tree indexes on the email column?
Answer: a standard B-tree index stores exact column values ordered alphabetically. Applying a function like lower with email transforms the values at runtime, preventing the database optimizer from using the standard index. To fix, you must create an expression or functional index explicitly on lower with email.
Follow up 3 curveball. What if creating an index reduces select query latencies from 12 seconds to 2 milliseconds, but write throughput insert or update drops by 30%? How do you resolve this index overhead?
Answer: every index on a table must be updated synchronously during insert, update, and delete operations. To resolve, eliminate redundant or unused indexes using database statistics pg_stat_user_ indexes. Create partial indexes covering only active rows, for example, where status equals active, or batch write operations.
Production Incident 66. A high concurrency payment settlement microservice throws frequent deadlock loser data access exception errors, Postgres SQL error. Deadlock detected. Customer payment transactions fail intermittently during peak sales events. As the on-call Java application support engineer, how do you resolve these database transactional deadlocks?
Answer: when concurrent database transactions fail due to row-level deadlocks, my priority is to analyze database lock dependency logs, enforce uniform row update acquisition ordering, and implement transaction retries using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application error logs using kubectl logs for deadlock loser data access exception or cannot acquire lock exception. 2. Check database APM metrics to measure the rate of aborted transactions and lock wait timeouts. 3. Confirm whether database deadlocks impact all payment workflows or specific multi-account settlement operations. Phase 2. Investigation and evidence gathering. 1. Retrieve detailed database deadlock logs from Postgres SQL pg_stat_activity or deadlock graph, or MySQL show engine in NoDB status. 2. Identify the 2 SQL statements and table rows involved in the circular lock wait graph. 3. Review Spring at transactional service methods to check row update sequencing across concurrent threads. Phase 3. Root cause analysis. 1. Evidence collected. Postgres SQL deadlock log showed transaction 1 updated account 1 then account 2, while transaction 2 updated account 2 then account 1. 2. Primary root cause. Inconsistent row lock acquisition order. Concurrent payment settlement transactions updated account row balances in reverse order, creating a classic circular database row lock wait that forced the database engine to terminate one transaction. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Configure Spring retry at retriable with value equals deadlock loser data access exception .class, max. Attempts equals 3 on payment settlement methods to retry deadlock transactions automatically. 2. Permanent resolution. Refactor code to sort primary key IDs, for example arrays .sort with account IDs before executing bulk row updates, guaranteeing uniform lock acquisition order. 3. Validation. Confirm 0 deadlock loser data access exception errors under high concurrency load tests and verify payment processing stability. Phase 5. Recurrence prevention. 1. Enforce consistent row access ordering across all services by sorting primary key IDs before multi-row update or select for update operations. 2. Configure Spring retry with exponential backoff on transient database lock acquisition exceptions. 3. Conduct deadlock simulation stress tests in staging prior to production releases. Pro tip interview insight. Database deadlocks occur when concurrent transactions lock rows in reverse order. Always sort primary key IDs, for example array.sort with account IDs, before executing multi-row update or select for update operations, guaranteeing that all transactions acquire database row locks in the exact same order.
Follow up when expected. A logical continuation of the incident. How does sorting entity IDs before executing multi-row update operations prevent database deadlocks?
Answer: database deadlocks require a circular wait condition. Transaction 1 locks row A, then wants row B. Transaction 2 locks row B, then wants row A. Sorting primary key IDs, for example. Ascending numerical order forces every transaction in the entire system to acquire row locks in the exact same order, mathematically eliminating circular wait conditions.
Follow up 2 deeper. Experienced tester. Why should transactions executing select for update use a short lock underscore timeout in Postgres SQL or in NoDB underscore lock underscore wait underscore timeout in MySQL?
Answer: without a lock timeout, a thread executing select for update waits indefinitely if another transaction holds the row lock, causing application connection pool exhaustion. Setting a short lock timeout, for example. Set lock underscore timeout equals 3000 forces the query to fail fast with a retrievable exception after 3 seconds.
Follow up 3 curveball. What if deadlocks occur on a table with an insert statement due to gap locking in MySQL in NoDB reproducible at read committed versus repeatable read isolation levels?
Answer: in MySQL in NoDB under repeatable read default, select for update or insert operations acquire gap locks to prevent phantom reads, which frequently deadlock under concurrent inserts. Switching transaction isolation level to read committed eliminates gap locks, preventing insert-level deadlocks.
Production Incident 67. After deploying a feature querying orders by customer underscore ID and created underscore at, database CPU utilization spikes to 100%, causing widespread application connection timeouts. APM traces show query latencies increasing exponentially as table row counts grow. As the on-call Java application support engineer, how do you resolve this missing index CPU spike?
Answer: when a missing foreign key index triggers database CPU saturation, my priority is to analyze active query locks, execute non-blocking online index creations, and enforce schema index validation using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check database server CPU utilization in Grafana to confirm 100% CPU saturation. 2. Inspect APM database execution traces to identify queries on the orders table experiencing latency spikes. 3. Confirm whether database CPU saturation triggers application-wide HTTP 503 connection pool timeouts. Phase 2. Investigation and evidence gathering. 1. Query active database statistics PG_stat_ statements in Postgres SQL or performance schema in MySQL to identify top CPU consuming queries. 2. Execute explain analyze on the order lookup query, filtering by customer underscore ID and created underscore at. 3. Review database table schema definitions to check if the foreign key column customer underscore ID lacks an explicit index. Phase 3. Root cause analysis. 1. Evidence collected. Explain analyze showed a full table scan on 50 million rows in orders during join operations with customers. 2. Primary root cause. Missing foreign key supporting index. The release introduced a query joining orders and customers on customer underscore ID without a supporting index on the foreign key column, forcing 50 million row nested loop scans and saturating database CPU. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Execute an online non-blocking index creation. Create index concurrently IDX underscore orders underscore customer underscore created on orders with customer underscore ID comma created underscore at to drop database CPU from 100% to 10% instantly. 2. Permanent resolution. Add the index definition to Flyway or Liquid-based database migration scripts. 3. Validation. Rerun, explain, analyze, verify execution plan uses the new index, and confirm database CPU usage normalizes. Phase 5. Recurrence prevention. 1. Enforce CI and CD schema linter rules, requiring explicit index definitions on all foreign key columns in database migration scripts. 2. Configure database performance monitoring alerts for full table scans on tables exceeding 100,000 rows. 3. Mandate index coverage audits prior to deploying new relational entity relationships. Pro tip: interview insight. Foreign key columns in relational databases do not automatically create indexes in many engines like PostgreSQL. Unindexed foreign keys cause full table scans during join operations and lock parent tables during deletes. Always explicitly index foreign key columns in your database migration scripts.
Follow up when expected. A logical continuation of the incident. Why does an unindexed foreign key column in a child table cause exclusive table locks on the child table when deleting rows from the parent table?
Answer. To enforce referential integrity during a parent row delete, the database engine must check if matching foreign key rows exist in the child table. Without an index on the child table foreign key, the database must scan or lock the entire child table, blocking concurrent child table writes.
Follow up to deeper. Experienced tester. What is a composite index, and why does column order matter in an index on customer_ID created _at?
Answer. A composite index combines multiple columns into a single index. Column order strictly follows the leftmost prefix rule. An index on customer_ID created _at can optimize queries filtering on customer_ID alone, or customer_ID and created _at, but cannot optimize queries filtering on created _at alone.
Follow up 3 curveball. What is a covering index, and how does it allow the database engine to execute index-only scans without reading the physical table heap?
Answer. A covering index includes all columns requested by a select query. For example, create index IDX on orders customer_ID include total _amount. The database answers the query directly from B-tree index pages without visiting table data blocks on disk, reducing I/O to near zero.
Production Incident 68. An analytics microservice running background report queries exhausts its database connection pool every 6 hours. APM dashboards show active connections climbing steadily until HikariCP throws connection is not available, request timed out after 30 seconds. As the on-call Java application support engineer, how do you resolve this connection leak?
Answer. When an application leaks database connections steadily over time, my priority is to enable HikariCP leak detection logging, locate unclosed JDBC resources, and enforce try with resources resource cleanup using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Grafana HikariCP active connection charts to confirm linear connection growth until reaching maximum pool size equals 20. 2. Check application error logs using kubectl logs for HikariCP connection pool timeout exceptions. 3. Confirm whether connection exhaustion affects all reporting pods or specific background execution nodes. Phase 2. Investigation and evidence gathering. 1. Enable HikariCP connection leak detection by setting spring.datasource.hikari.leak detection threshold equals 2002 seconds via config map. 2. Inspect application logs for HikariCP warning stack traces containing apparent connection leak detected. 3. Review raw JDBC code in reporting repositories for data source.getConnection or result set calls. 4. Check whether unhandled exceptions in custom reporting logic bypass connection close statements. Phase 3. Root cause analysis. 1. Evidence collected. HikariCP leak log showed apparent connection leak detected on thread HTTP neo 8080 exec 3, originating from raw report repository.fetch summary. 2. Primary root cause. JDBC connection leak. A custom reporting method obtained raw JDBC connection and result set instances directly from data source without wrapping them in try with resources blocks, preventing connection return to HikariCP. Phase 4. Resolution and Service Restoration. 1. Immediate recovery. Reduce MTTR. Perform a rolling pod restart using kubectl rollout restart to flush leaked connections and restore immediate reporting service. 2. Permanent resolution. Wrap all raw JDBC connection, statement, and result set instantiations in try with resources blocks or refactor to Spring JDBC template. 3. Validation. Confirm HikariCP active connection metrics stabilize at 3 connections post-report execution and leak warnings disappear. Phase 5. Recurrence prevention. 1. Keep HikariCP leak detection threshold enabled in staging and production environments using an appropriate threshold that balances diagnostics and false positives. 2. Enforce static code analysis rules sonar cube flagging unclosed auto-closable JDBC resources. 3. Standardize Spring JDBC template or Spring Data JPA for all database interactions. Pro tip interview insight. A connection leak occurs when application code borrows a connection from the pool but fails to close or return it. Always set leak detection threshold equals 2000 in HikariCP. When a thread holds a connection longer than 2 seconds, HikariCP logs the exact stack trace of the leaking method.
Follow up when expected. A logical continuation of the incident. Why does wrapping JDBC connection, statement, and result set in try with resources guarantee resource cleanup, even during runtime exceptions?
Answer. Java's try with resources statement implements the auto-closable interface. The JVM automatically generates implicit finally blocks that invoke close on all declared resources in reverse order of creation, guaranteeing connection return to HikariCP, even if an unhandled runtime exception occurs.
Follow up deeper. Experience tester. How does Spring JDBC template eliminate connection leak risks compared to writing raw JDBC code?
Answer. Spring JDBC template manages the complete JDBC resource lifecycle internally. It acquires connections from data source, executes SQL statements, handles exception translation, and automatically closes result set, statement, and connection resources in guaranteed internal finally blocks.
Follow up 3 curveball. What if HikariCP reports 0 connection leaks, but database server connection limits are exhausted by hundreds of idle connections from scaling microservice pods?
Answer. This is database connection bloat caused by over-provisioned pool sizes across scaled pod replicas. For example, 50 pods with max pool size equals 20 equals 1,000 connections. To fix, reduce maximum pool size to 5 per pod, configure HikariCP idle timeout, or deploy a database proxy like PG Bouncer to multiplex client connections.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 69. A complex order placement workflow fails, throwing unexpected rollback exception. Transaction rolled back because it has been marked as rollback only. Customer orders are canceled, even though logs show the outer at transactional method caught and handled the internal exception. As the on-call Java application support engineer, how do you resolve this transaction rollback failure?
Answer. When an intertransactional exception marks a shared physical transaction as rollback only causing unexpected rollback exception, my priority is to inspect Spring transaction boundaries, configure propagation rules, and isolate nested transactions using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application logs via kubectl logs to confirm org.springframework.transaction.unexpected rollback exception. 2. Trace the order placement workflow execution path to identify which nested service method threw the caught exception. 3. Confirm whether order cancellation impacts all checkout attempts or specific payment processing paths. Phase 2. Investigation and evidence gathering. 1. Review Spring service method call chains for nested at transactional annotations. 2. Check inner service methods, for example audit log service.log, for caught runtime exceptions that were suppressed by outer try-catch blocks. 3. Inspect Spring Transaction Manager logs logging.level.org.springframework.transaction equals debug to trace physical transaction boundary state. Phase 3. Root cause analysis. 1. Evidence collected. Transaction logs showed audit log service.log through a data access exception marked rollback only, which order service.place order caught in a try-catch block. 2. Primary root cause. Rollback only transaction state. The inner and outer at transactional methods shared the same physical database transaction. When the inner method threw an exception, Spring's transaction manager marked the shared physical transaction as rollback only, forcing unexpected rollback exception when the outer method attempted to commit. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Annotate the inner service method with at transactional with propagation equals propagation dot. Requires underscore new to execute the inner operation in an isolated physical transaction, then perform a rolling deployment. 2. Permanent resolution. Refactor non-critical audit logging operations to run asynchronously using Spring at async or dedicated non-transactional helper beans. 3. Validation. Confirm orders complete successfully even if audit logging fails and verify 0 unexpected rollback exception occurrences. Phase 5. Recurrence prevention. 1. Establish team coding guidelines requiring explicit propagation dot. Requires underscore new or non-transactional handling for optional nested service operations. 2. Implement mandatory integration tests asserting parent transaction, commit behavior when nested operations fail. 3. Configure static code analysis rules flagging caught runtime exceptions inside nested at transactional methods. Pro tip interview insight. By default, nested Spring at transactional methods share the same physical database transaction. If an inner method throws a runtime exception, Spring marks the physical transaction as rollback only, even if the outer method catches the exception. Use propagation dot requires underscore new if the inner operation should fail independently.
Follow up when expected. A logical continuation of the incident. How does Spring's default transaction propagation dot required manage physical database transactions across nested service calls?
Answer: propagation dot required is Spring's default. If an active physical transaction exists, the nested method joins that same transaction. If an exception occurs in the nested method, Spring marks the shared physical transaction as rollback only, guaranteeing that the entire transaction rolls back upon completion.
Follow up 2 deeper. Experienced tester. How does propagation dot requires new differ from propagation dot nested in Spring transaction management?
Answer: propagation dot requires new suspends the outer transaction and opens a completely independent physical database connection. Propagation dot nested uses JDBC save points within the same physical connection, allowing the nested block to roll back to a save point without rolling back the outer transaction.
Follow up 3 curveball. What happens if an inner method annotated with at transactional with propagation equals propagation dot requires new throws an exception? Does the outer transaction still roll back?
Answer: yes, if the outer method allows the exception to propagate up, requires underscore new executes in an independent physical transaction that rolls back immediately. However, if the outer method catches that exception in a try-catch block, the outer transaction remains clean and can commit successfully.
Production incident 70. After an e-commerce user updates their profile address, the web application redirects them to their profile dashboard, but the page displays their old address. Refreshing 5 seconds later shows the updated address. As the on-call Java application support engineer, how do you resolve this database replication lag issue?
Answer: when database replication lag causes stale data reads immediately after write operations, my priority is to inspect replica sync delays, implement read after write consistency routing, and enforce sticky read routing using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect database replication, lag metrics in Grafana PG_stat_replication byte lag, or MySQL seconds _behind _master. 2. Check application, routing logs to confirm read queries for profile dashboards are directed to read replicas. 3. Confirm whether stale data issues are isolated to immediate post-write redirects or affecting all read operations. Phase 2. Investigation and evidence gathering. 1. Inspect Spring Data Source Routing configurations lazy connection data source router or at transactional with read only equals true annotations. 2. Check primary master database write transaction volume and network throughput between master and read replica hosts. 3. Measure exact replication lag time on read replicas during peak user update windows. Phase 3. Root cause analysis. 1. Evidence collected. PostgreSQL replication lag metrics showed read replicas lagging behind primary master by 2.4 seconds during peak write periods. 2. Primary root cause. Asynchronous replication lag. The profile update wrote to primary master, but the immediate dashboard redirect executed at transactional with read only equals true query against a read replica that was 2.4 seconds behind master. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Route read after write requests temporarily to the primary database by bypassing replica routing, for example, disabling read-only routing for affected endpoints, then perform a rolling deployment if configuration changes are required. 2. Permanent resolution. Implement read after write sticky session, routing all user read queries to primary master for 5 seconds following any write operation by that user. 3. Validation. Confirm 100% data consistency on post-update redirects, verify read replica lag normalizes, and monitor master database load. Phase 5. Recurrence prevention. 1. Configure custom Spring lazy connection data source router with user session sticky read after write routing logic. 2. Set Prometheus or Grafana alerts for database replication lag exceeding 1 second. 3. Optimize read replica write replay performance and network bandwidth between database nodes. Pro tip interview insight. In master replica database architectures, read replicas asynchronous replication introduces replication lag. Never execute immediate read after write queries against read replicas. Route post-write reads to the master database or implement sticky session routing for a few seconds after a write.
Follow-up 1 expected. A logical continuation of the incident. How does Spring's lazy connection data source router route read-only transactions to read replicas versus master databases?
Answer. Lazy connection data source router inspects Spring's transaction synchronization manager. Is current transaction read-only. If read-only equals true, it fetches a JDBC connection from the read replica pool. Otherwise, it routes to the master database pool. Connection acquisition is deferred lazily until the first SQL query executes.
Follow-up 2 deeper. Experienced tester. How do you implement read after write consistency using session tokens or Redis timestamps?
Answer. Upon executing a write operation, set a user session attribute or Redis key user :123 last underscore write equals timestamp. When servicing subsequent read queries, check the timestamp. If the write occurred within the last 5 seconds or replica lag duration, route the read query to master. Otherwise, route to read replicas.
Follow-up 3 curveball. What if a read replica database crashes completely? How should lazy connection data source router handle replica pool failover without crashing web requests?
Answer. If a read replica fails, the routing data source must catch connection acquisition exceptions and automatically fail over to alternative healthy read replicas or the primary master database. Combining routing data sources with connection pool health checks ensures seamless high availability reads.
Production Incident 71. An API endpoint returning a list of 100 customer orders degrades severely, taking 8 seconds to respond. APM traces reveal that fetching 100 orders executed 101 separate SQL queries against the database, exhausting connection pools, and driving up database CPU. As the on-call Java application support engineer, how do you resolve this N+1 query storm?
Answer. When ORM lazy loading triggers N+1 seconds QL queries degrading API response times, my priority is to inspect query execution traces, enforce join fetch or entity graph fetch strategies, and eliminate query storms using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect a PM database transaction, traces to confirm high query counts per HTTP request, 101 SQL queries for one request. 2. Check database query execution, throughput metrics in Grafana to verify query volume spikes. 3. Confirm whether API response latency degradation impacts order list endpoints specifically. Phase 2. Investigation and evidence gathering. 1. Enable SQL logging and staging Spring.jpa.show SQL equals true to view generated Hibernate SQL statements. 2. Inspect JP, a entity relationship annotations at many-to-one, at one-to-many on order and customer classes. 3. Review Spring Data JPA repository queries to check if list methods use default find all without fetch joins. Phase 3. Root cause analysis. 1. Evidence collected. SQL logs showed one initial select query on orders, followed by 100 individual select star from customer where ID equals ? Queries executed sequentially. 2. Primary root cause. Hibernate N+1 query problem. Fetching a list of 100 order entities, executed one query for the parent list, plus 100 individual SQL queries, to lazily load the associated customer entity inside a loop. Overwhelming database connections. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Replace the affected repository query with a JPQL join fetch or add entity graph implementation to eliminate the N+1 query pattern immediately, then perform a rolling deployment. 2. Permanent resolution. Audit all repository list queries across microservices to enforce join fetch or add entity graph annotations. 3. Validation. Confirm SQL query count drops from 101 to 1 query, API response times drop from 8 seconds to 15 milliseconds, and database CPU normalizes. Phase 5. Recurrence prevention. 1. Integrate Hibernate query count assertion tools such as QuickPerf into CI and CD build pipelines to fail builds if query counts exceed threshold limits. 2. Configure APM alerts monitoring SQL queries per HTTP request ratios. 3. Enforce mandatory JPA entity fetch strategy reviews and team pull requests. Pro tip interview insight. The Hibernate N+1 query problem occurs when fetching N entities triggers one query for the parent list, plus N separate queries for child relationships. Always use join fetch in JPQL or Spring Data JPA. Add entity graph on list queries to fetch parent and child entities in a single SQL query.
Follow up when expected. A logical continuation of the incident. What is the difference between join fetch in JPQL and add entity graph in Spring Data JPA when solving N+1 queries?
Answer. Join fetch explicitly specifies inner or left join fetches in custom JPQL query strings. Spring Data JPA at entity graph with attribute paths equals customer achieves the same single query eager fetching declaratively on generated repository methods without requiring custom JPQL query strings.
Follow up 2 deeper. Experience tester. Why does changing fetch type from eager to lazy on at many to one relationships not automatically solve the N+1 query problem?
Answer. Changing fetch type to lazy defers child entity loading until getter methods are called. However, if your service iterates through the parent list and calls order.getCustomer.getName, Hibernate still executes N individual SQL select queries to fetch customer details for each order inside the loop.
Follow up 3 curveball. What is the multiple bag fetch exception in Hibernate, and why can you not use join fetch on 2 separate at one to many list collections in the same query?
Answer. Hibernate throws multiple bag fetch exception if a query attempts to join fetch 2 unordered lists at one to many collections simultaneously. This causes a Cartesian product explosion in memory. To solve, change list to set or use at batch size with size equals 20 to batch child queries.
Production Incident 72. A high-throughput session and caching microservice starts throwing Redis command timeout exception and Jedi's connection exception. APM dashboards show active Redis client connection pools, saturated at 100% capacity 50 out of 50 connections occupied, blocking HTTP worker threads. As the on-call Java application support engineer, how do you resolve this Redis connection exhaustion?
Answer: when Redis client connection pools exhaust while HTTP worker threads block, my priority is to inspect active Redis commands, kill blocking single-threaded operations, and enforce non-blocking key scanning using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Redis client pool metrics in Grafana to confirm active connections equal maximum capacity Redis pool active equals 50. 2. Check application logs using kubectl logs for Redis command timeout exception or Jedi's connection exception stack traces. 3. Confirm whether Redis connection exhaustion impacts all microservice replicas or specific caching tiers. Phase 2. Investigation and evidence gathering. 1. Inspect Redis server metrics info clients to check connected client counts and slow command logs slow log get 10. 2. Check application source code for unbounded key star commands executed on production Redis instances. 3. Review Redis connection pool settings in application.yml spring.data.redis.ledis.pool.max active. Phase 3. Root cause analysis. 1. Evidence collected. Redis slow log showed keys user : taking 10.2 seconds, holding the single-threaded Redis event loop. 2. Primary root cause. Redis command blocking. A custom admin dashboard endpoint executed an unbounded keys user : command on production Redis, locking the single-threaded Redis server event loop for 10 seconds and exhausting all client pool connections. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Identify the client executing the blocking keys command using client list. Terminate the offending client connection using client kill if required. Temporarily increase Redis max active only if Redis has sufficient capacity, and perform a rolling restart if necessary. 2. Permanent resolution. Replace keys commands with non-blocking iterative scan calls or Redis sets and disable dangerous commands in redis.conf. 3. Validation. Confirm Redis active connections drop to baseline 5 connections, command timeouts clear and cache hit rates normalize. Phase 5. Recurrence prevention. 1. Disable dangerous Redis commands rename command keys and rename command flushall in production redis.conf. 2. Enforce scan-based cursor iteration instead of keys across all custom Redis repositories and administrative tooling. 3. Set Prometheus alerts for Redis connection pool utilization exceeding 80% of max active limits. Pro tip interview insight. Redis is single-threaded for command execution. Never run keys star in production environments as it locks the single-threaded Redis event loop, causing client connection timeouts and pool exhaustion across all microservices. Always use scan for iterative key scans.
Follow up when expected. A logical continuation of the incident. How does Redis differ from Jedi's in Spring Data Redis regarding thread safety and connection pooling?
Answer: Redis is built on Netty and shares a single, thread-safe connection across multiple threads asynchronously by default. Jedi's is synchronous and not thread-safe, requiring a dedicated pooled connection per thread Jedi's pool. Redis only requires connection pooling when executing blocking transactional operations.
Follow up 2 deeper. Experienced tester. Why should commands like keys, flushall, and flushdb be disabled in production redis.conf using rename command?
Answer: key star iterates sequentially through every key in Redis, holding the single-threaded event loop O of n time. Flushall deletes all keys across all databases synchronously, blocking the server for seconds or minutes. Disabling or renaming them in redis.conf prevents accidental or malicious execution.
Follow up 3 curveball. What if Redis connection pool exhaustion occurs due to Redis Netty event loop thread starvation rather than an undersized pool?
Answer: if netty event loop threads are starved by blocking calls in custom reactive pipelines, Redis cannot process Redis response callbacks, causing client command timeouts despite free pool connections. To fix, avoid blocking operations in reactive streams or isolate blocking code using schedulers. Bounded elastic.
Production Incident 73. During peak business hours, a highly requested product catalog cache key expires. Immediately, 5,000 concurrent HTTP requests miss the cache simultaneously, sending 5,000 identical heavy SQL queries to the primary database within 500 milliseconds and crashing the database host. As the on-call Java application support engineer, how do you resolve this cache stampede?
Answer: when a hot cache key expiration triggers a cache stampede overloading the primary database, my priority is to pre-warm the hot key, enforce application-level sync locking, and implement probabilistic early expiration using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Correlate database CPU spikes and connection pool exhaustion in Grafana with a specific cache key TTL expiration timestamp. 2. Inspect APM traces to confirm a thundering herd pattern where thousands of threads execute identical SQL queries. 3. Confirm whether database crash impacts the entire platform or specific product catalog APIs. Phase 2. Investigation and evidence gathering. 1. Review Spring caching annotations at cacheable on product catalog service.getCatalog. 2. Check whether at cacheable uses the sync equals true attribute to synchronize cache recomputations. 3. Inspect database active query tables PG_stat_activity to confirm thousands of identical select queries executing concurrently. Phase 3. Root cause analysis. 1. Evidence collected. Database logs showed 5,000 concurrent select star from product_catalog, where ID equals 1001 queries executed within 500 milliseconds. 2. Primary root cause. Cache stampede thundering herd. A hot product catalog key expired without mutual exclusion locking sync equals true or early expiration, causing thousands of concurrent request threads to miss the cache simultaneously and crash the primary database. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Pre-warm the hot product catalog key manually in Redis set product:catalog:1001. Temporarily rate limit incoming requests or enable request throttling for the affected endpoint, allowing the primary database to recover from overload. 2. Permanent resolution. Enable Spring at cacheable with sync equals true on hot cache methods, or implement a distributed lock redison so only one thread recomputes the cache while others wait. 3. Validation. Confirm database CPU drops to 15%, cache hit rates reach 99.9%, and product catalog latency stays under 5 milliseconds. Phase 5. Recurrence prevention. 1. Mandate at cacheable with sync equals true across all high-traffic cache annotations in microservice codebases. 2. Implement probabilistic early expiration xfetch algorithm for hot cache keys to refresh values before hard TTL expiration. 3. Pre-warm hot cache keys automatically prior to scheduled marketing sales events. Pro tip interview insight. Cache stampede occurs when a hot cache key expires and thousands of concurrent requests miss the cache simultaneously, overwhelming the database. Always configure Springs at cacheable with sync equals true or use a distributed lock like redison, so only one thread recomputes the cache while others wait.
Follow up when expected. A logical continuation of the incident. How does Springs at cacheable with sync equals true attribute prevent cache stampede at the application JVM level?
Answer: when sync equals true is enabled, Spring's cache interceptor uses local synchronized locking per cache key. The first thread that misses the cache acquires the lock and computes the value from the database, while all other concurrent threads wait locally. Once computed, waiting threads read the value directly from cache without hitting the database.
Follow up 2 deeper. Experience tester. What is probabilistic early expiration X-fetch algorithm, and how does it prevent thundering herds on hot cache keys?
Answer: Xfetch calculates a probabilistic recomputation chance based on remaining TTL and computation time. As a hot key nears expiration, random requests periodically recompute and refresh the cache in the background before hard TTL expires, completely eliminating cache miss spikes.
Follow-up 3 curveball. What if the single thread recomputing the cache key throws an exception or hangs on a slow database query? How do you prevent waiting threads from deadlocking?
Answer: use a distributed lock with a strict lock lease timeout. For example, Redis and try lock with 2 seconds, 5 seconds. If the lock owner thread hangs or crashes, the lock automatically releases after 5 seconds, allowing another waiting thread to acquire the lock and attempt recomputation, preventing thread deadlocks.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 74. A customer updates their subscription billing address, receives a success confirmation, but the profile page continues serving old billing data for hours. Support tickets surge as users see stale information across microservice portals. As the on-call Java application support engineer, how do you resolve this cache inconsistency?
Answer: when cache inconsistency serves stale data following database updates, my priority is to inspect cache eviction triggers, enforce transactional event listeners, and align cache invalidation with database commits using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Verify stale reads by comparing Redis cached values get user:1001 profile against primary database records. Select star from users where ID equals 1001. 2. Check application error logs using kubectl logs for failed cache eviction exceptions. 3. Confirm whether cache inconsistency affects all user updates or specific multi-step profile workflows. Phase 2. Investigation and evidence gathering. 1. Review Spring caching annotations at cache evict, at cache put, at cacheable on user profile update service methods. 2. Check whether cache eviction is executed before or after the primary database transaction commits. 3. Inspect message queue consumers responsible for publishing cache invalidation events across microservice regions. Phase 3. Root cause analysis. 1. Evidence collected. Redis audit logs showed no del user:1001 profile command executed during profile update transactions. 2. Primary root cause. Missing cache invalidation event. The profile update service modified the primary database record, but failed to trigger at cache evict or publish a cache invalidation event because eviction logic was omitted from the update pipeline. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Manually invalidate the stale key in Redis del user:1001 profile and flush affected profile cache namespaces. 2. Permanent resolution. Implement at transactional event listener with phase equals after underscore. Commit to guarantee cache eviction events. Publish only after the database write transaction successfully commits. 3. Validation. Update user profile, verify Redis key is evicted instantly post-commit, and confirm subsequent reads reflect fresh database data. Phase 5. Recurrence prevention. 1. Mandate at transactional event listener with phase equals after underscore commit for all cache eviction event publishers. 2. Configure reasonable TTL values as a safety fallback, while treating TTL as a secondary protection rather than the primary cache invalidation mechanism. 3. Implement automated cache consistency verification integration tests in CI and CD pipelines. Pro tip interview insight. Cache inconsistency happens when database records update, but the cache is not invalidated. Never invoke at cache evict before database commit. Always use springs at transactional event listener with phase equals transaction phase dot after underscore. Commit to publish cache eviction events only after the database write transaction successfully commits.
Follow up when expected. A logical continuation of the incident. What is the difference between cache aside, write through, and write behind caching patterns?
Answer: in cache aside, the application reads from cache on miss. It loads from DB and populates cache. In write through, the application writes to cache, and cache synchronously writes to DB before returning. In write behind write back, the application writes to cache, and cache asynchronously flushes writes to DB in background batches.
Follow up 2 deeper. Experienced tester. Why can invoking at cache evict inside a transactional method cause cache inconsistency if the database transaction subsequently rolls back?
Answer: if at cache evict executes during the transaction, and the transaction later rolls back, for example, due to a constraint violation, the database changes are undone, while the cache remains evicted or populated with uncommitted data, causing stale or phantom reads for other threads.
Follow up 3 curveball. How do you maintain cache consistency across a multi-region microservice deployment where Redis clusters are replicated asynchronously?
Answer: use two-phase cache invalidation or pub sub-event broadcasting like Redis pub sub or Kafka. When a write occurs in region A, publish an invalidation event to Kafka. All regional consumers invalidate their local Redis keys, ensuring multi-region cache consistency within milliseconds.
Production Incident 75. A nightly financial reconciliation Spring batch job fails midway through processing a 10 million row file due to a transient database glitch. When the automated scheduler attempts to restart the job, it throws job instance, already complete exception or job execution, already running exception, and refuses to resume. As the on-call Java application support engineer, how do you resolve this batch restart failure?
Answer: when a Spring batch job refuses to restart due to corrupted metadata states, my priority is to inspect Spring batch execution tables, update stale job execution statuses, and resume execution from the last valid chunk checkpoint using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Spring batch execution logs in Splunk to confirm job execution, already running exception, or job instance, already complete exception. 2. Query Spring batch metadata, tables batch underscore job underscore execution, and batch underscore job underscore instance to check the last recorded execution state. 3. Confirm whether batch pipeline failure impacts downstream morning financial reporting workflows. Phase 2. Investigation and evidence gathering. 1. Inspect batch underscore job underscore execution table, rows where status equals started and end underscore time is null for the failed job execution ID. 2. Verify whether the batch pod container was killed abruptly by Kubernetes killed or pod eviction during execution. 3. Check batch underscore step underscore execution table to locate the exact chunk commit count where processing halted. Phase 3. Root cause analysis. 1. Evidence collected. Batch underscore job underscore execution table showed status equals started for job execution ID 101, despite the pod terminating 2 hours earlier. 2. Primary root cause. Corrupted metadata state. The batch container was terminated abruptly during rolling updates without updating batch underscore job underscore execution status to failed, causing Spring batch to reject restarts, believing the job was still actively running. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Manually update Spring batch metadata update batch underscore job underscore execution set status equals failed exit underscore code equals failed where job underscore execution underscore ID equals 101 and re-trigger job execution to resume from the last save chunk checkpoint. 2. Permanent resolution. Implement Kubernetes SIG term aware graceful shutdown together with Spring batch job execution, listener callbacks, so the application can gracefully stop running jobs and update batch underscore job underscore execution status to failed before container termination whenever possible. 3. Validation. Confirm batch job resumes from chunk 4500, processes remaining records, and completes with status equals completed. Phase 5. Recurrence prevention. 1. Implement automated pre-start metadata cleanup scripts that mark orphan started job executions as failed prior to scheduler execution. 2. Ensure all batch step item readers implement stateful item stream restartability. 3. Configure unique daily job parameters using Run ID Incrementer to prevent instance collision errors. Pro tip interview insight. Spring Batch uses metadata tables batch_job_execution to track step checkpoints and restartability. If a container is killed abruptly, the job execution status remains stuck in started. You must update the metadata status to failed before Spring Batch allows the job instance to resume from its last chunk checkpoint.
Follow-up when expected. A logical continuation of the incident. How does Spring Batch's execution context enable restartability from the exact failed chunk position during batch job re-execution?
Answer: during chunk processing, item stream.update periodically saves reader progress, for example, current line number or record ID into the batch_step_execution_context table. On restart, Spring Batch passes the saved execution context back to the item reader, allowing it to skip already committed records and resume from the exact failure point.
Follow-up 2 deeper. Experienced tester. What is the difference between a job instance and a job execution in Spring Batch, and how do job parameters define job uniqueness?
Answer: a job instance represents a logical batch job run identified by its name and unique job parameters, for example, date equals August 1st, 2026. A job execution represents a single physical attempt to run a job instance. If a job execution fails, a new job execution is created under the same job instance upon restart.
Follow-up 3 curveball. How do you design Spring Batch item writer steps to be idempotent so that reprocessing a partially executed chunk does not create duplicate database records?
Answer: use database upsert operations like PostgreSQL on conflict do update or MySQL insert, on duplicate key update or business key deduplication in item writer. Alternatively, wrap item writing in transactional chunk boundaries, so chunk failures trigger full transaction rollbacks before checkpointing.
Production Incident 76. An enterprise reporting microservice running Quartz scheduler triggers automated billing report jobs twice at the exact same minute. APM traces show duplicate billing emails and double customer invoices generated every morning. As the on-call Java application support engineer, how do you resolve this duplicate Quartz execution?
Answer: when Quartz scheduler triggers duplicate job runs across cluster nodes, my priority is to verify clustered job store configurations, sync server NTP clocks, and enforce database lock coordination using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application logs across all Quartz pod replicas using kubectl logs to confirm duplicate trigger firings at the exact same second. 2. Check database audit tables to quantify duplicate billing invoice creation. 3. Verify whether duplicate firings affect all scheduled jobs or specific reporting triggers. Phase 2. Investigation and evidence gathering. 1. Inspect Quartz cluster configuration properties in application.yml.org.quartz.jobstore is clustered. 2. Check Quartz metadata lock tables QRTZ_locks, QRTZ_triggers, QRTZ_fired_triggers in the primary database. 3. Verify NTP clock synchronization across Kubernetes worker nodes using chronic tracking or NTP stat. Phase 3. Root cause analysis. 1. Evidence collected. Quartz properties showed org.quartz.jobstore. is clustered equals false deployed across 3 pod replicas. 2. Primary root cause. Quartz cluster misconfiguration. Multiple application pod replicas ran Quartz scheduler with is clustered equals false, causing each node to operate as an independent standalone scheduler and fire the same trigger simultaneously. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Enable Quartz clustering org.quartz.jobstore. is clustered equals true in config map properties and perform a rolling pod restart to synchronize trigger locks. 2. Permanent resolution. Ensure Quartz uses a database-backed jobstore TX or jobstore CMT with explicit cluster check in intervals. 3. Validation. Confirm Quartz logs show cluster manager, node check incomplete, and verify 0% duplicate job firings. Phase 5. Recurrence prevention. 1. Enforce clustered quartz configuration properties in base application archetype templates. 2. Synchronize container node clocks using host and TP daemon tracking across all Kubernetes worker nodes. 3. Set Prometheus alerts monitoring QRTZ_fired_triggers for duplicate trigger execution entries. Pro tip interview insight. Quartz scheduler running across multiple pod replicas must have org.quartz.jobstore. Is clustered equals true configured alongside a database-backed jobstore tx or jobstore CMT. Without clustering enabled, every pod operates as an isolated scheduler, causing duplicate job firings.
Follow up when expected. A logical continuation of the incident. How does Quartz clustered jobstore TX use row-level database locks in QRTZ_locks to coordinate trigger firings across cluster nodes?
Answer. When a trigger fires, Quartz acquires a row-level database lock in QRTZ_locks trigger_access. The node that successfully acquires the row lock updates the trigger state to acquired in QRTZ_triggers and executes the job. Other nodes fail to acquire the lock and skip execution.
Follow up deeper. Experienced tester. What is a Quartz misfire instruction, and how do you configure misfire handling when a node is offline during a scheduled trigger window?
Answer. A misfire occurs when a trigger misses its scheduled fire time, for example, due to a node crash or pool exhaustion. Quartz misfire instructions like misfire_instruction, _do_nothing, or misfire_instruction, now instruct Quartz whether to catch up, missed firings, or ignore them upon node recovery.
Follow up 3 curveball. What if NTP clock drift between Kubernetes worker nodes causes Quartz nodes to miscalculate cluster check-in intervals, marking healthy nodes as dead and triggering duplicate job executions?
Answer. If clock drift exceeds cluster check-in interval default 20 seconds, Quartz nodes falsely assume peer nodes died and forcibly release their locks, causing duplicate job firings. To fix, enforce active host NTP synchronization crony and set cluster check-in interval higher than maximum expected clock drift.
Production Incident 77. A Spring Batch ETL pipeline processing daily bank transaction. Files crashes with java.lang. Out-of-memory error Java heap space when processing a 5 GB CSV file containing 20 million records. As the on-call Java application support engineer, how do you resolve this batch heap exhaustion?
Answer. When a batch file processing job crashes with out-of-memory error due to loading entire files into heap, my priority is to replace in-memory file loading with Spring Batch chunk-oriented streaming readers using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect batch crash logs using kubectl logs to confirm java.lang. Out-of-memory error Java heap space. 2. Check container memory usage in Grafana to verify heap exhaustion during the file import step. 3. Confirm whether batch failure blocks downstream daily financial ledger processing. Phase 2. Investigation and evidence gathering. 1. Inspect Spring Batch step implementation code for custom tasklets using files.read_all-lines or bufferedreader.lines.collect. 2. Review Spring Batch item reader configuration to verify if streaming flat file item reader or chunk-oriented processing is used. 3. Check heapdump.hprof files in Eclipse MAT to identify top memory accumulators. Phase 3. Root cause analysis. 1. Evidence collected. Heap dump showed 4.2 GB of heap consumed by a single array list of string instantiated in file import tasklet. 2. Primary root cause. In memory file loading, a custom batch tasklet read the entire 5 GB CSV file into a java.util.list in memory using files.read_all-lines, instead of using Spring Batch streaming flat file item reader with chunk processing, exhausting heap memory. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily increase JVM heap-XM x8G and Kubernetes container memory limits only to complete the urgent batch execution. Then perform a rolling restart while planning a streaming-based fix. 2. Permanent resolution. Refactor batch step to use flat file item reader with chunked processing chunk with 1000, processing and committing 1000 records at a time. 3. Validation. Rerun batch file processing on the 5 GB file, verify heap usage remains flat below 500 MB, and confirm job completes. Phase 5. Recurrence prevention. 1. Prohibit files.read all lines or buffered reader.lines. Collecting code reviews for batch file processing. 2. Mandate chunk-oriented Spring batch step architecture across all file processing pipelines. 3. Conduct large file load testing and staging using multi-gigabyte synthetic CSV datasets. Pro tip interview insight. Never read large batch files into memory lists using files.read all lines or buffered reader.lines. Collect. Always use Spring batch chunk-oriented processing with flat file item reader, streaming and processing records in small chunks, for example, 1000 records, to keep memory usage constant regardless of file size.
Follow up when expected. A logical continuation of the incident. How does Spring Batch chunk-oriented processing item reader to item processor to item writer maintain a constant memory footprint during multi-gigabyte file processing?
Answer: chunk-oriented processing reads, transforms, and writes records in small configured batches. For example, chunk size equals 1000. After writing each chunk, Spring Batch commits the database transaction, clears the persistence context, and garbage collects processed items, keeping heap memory constant regardless of total file size.
Follow up 2 deeper. Experience tester. How do you configure partition steps in Spring Batch to process a 5 GB CSV file in parallel across multiple worker threads or pods?
Answer: use a multi-resource partitioner or simple partitioner to split the 5 GB file into smaller file chunks. The master step assigns partitioned file chunks to worker threads via task executor or worker pods via remote chunking, allowing parallel execution while maintaining chunk-level restartability.
Follow up 3 curveball. What if a single bad record in a 20 million row CSV file throws a parsing exception? How do you configure Spring Batch skip policies to prevent full job crashes?
Answer: configure skip fault tolerance on the batch step. Step builder.fault-tolerant.skip with flat file parse exception.class.skip limit with 10. When a parsing error occurs, Spring Batch logs the bad record, skips it, and continues processing up to the skip limit threshold without failing the entire job.
Production Incident 78. During a flash sale event, an inventory update microservice throws thousands of object optimistic locking failure exception errors. JP, a optimistic lock exception. API response times degrade as retry loops fail, causing 40% of customer checkout requests to fail. As the on-call Java application support engineer, how do you resolve these optimistic locking failures?
Answer: when high concurrent updates trigger JPA optimistic locking failures, my priority is to analyze version contention, switch high contention updates to atomic database operations, and restore transaction throughput using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application logs via kubectl logs for object optimistic locking failure exception or stale object state exception. 2. Check Grafana error metrics to confirm 40% transaction failure rates on inventory update APIs. 3. Confirm whether locking conflicts impact all catalog items or specific flash sale product IDs. Phase 2. Investigation and evidence gathering. 1. Inspect JPA entity classes for @version annotation definitions on the inventory class. 2. Review database query execution, logs for update statements, evaluating version numbers, update inventory set stock equals, parameter comma version equals 2, where ID equals parameter and version equals 1. 3. Analyze retry loop configurations on inventory update service methods. Phase 3. Root cause analysis. 1. Evidence collected. Database query logs showed 500 concurrent threads attempting to update version equals 1 on product ID 1001 simultaneously. 2. Primary root cause. High contention optimistic lock conflicts. Hundreds of concurrent HTTP worker threads attempted to update the exact same popular inventory row simultaneously, using JPA at version optimistic locking, causing all but one thread to fail with object optimistic locking failure exception. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Configure bounded Spring retry at retriable with value equals object optimistic locking failure exception class. Max attempts equals 5 with exponential backoff only for transient optimistic locking failures, then perform a rolling deployment. 2. Permanent resolution. Switch high contention inventory updates from optimistic locking to atomic database. Updates update inventory set stock equals stock -1, where ID equals parameter and stock is greater than 0 or pessimistic locking pessimistic _ right. 3. Validation. Confirm 0 object optimistic locking failure exception errors under load. Verify checkout success rates reach 100% and monitor latencies. Phase 5. Recurrence prevention. 1. Enforce atomic SQL update queries for all high contention counter and inventory stock operations. 2. Reserve JPA at version optimistic locking strictly for low concurrency entity editing workflows. 3. Mandate high concurrency stress testing and staging to detect optimistic lock contention pre-release. Pro tip interview insight. JPA optimistic locking at version is designed for low concurrency entity updates. Under high concurrency like flash sales, optimistic locking causes massive retry storms and transaction failures. Switch high contention updates to atomic SQL queries, for example update stock equals stock -1 or pessimistic locking.
Follow up when expected. A logical continuation of the incident. What is the fundamental difference between optimistic locking at version and pessimistic locking pessimistic, right in JPA or Hibernate?
Answer. Optimistic locking at version assumes no conflicts will occur. It checks version numbers upon commit, throwing an exception if another thread modified the row. Pessimistic locking pessimistic right acquires an immediate select for update database row lock when reading, blocking other threads until the transaction completes.
Follow up 2 deeper. Experienced tester. How do atomic database updates update inventory set stock equals stock -1, where stock is greater than 0, eliminate both optimistic and pessimistic locking overhead?
Answer. Atomic database updates execute directly at the SQL engine level. The database acquires a brief row lock only for the duration of the single update statement, decrementing stock atomically and returning affected row counts. This avoids Java entity version checks and long select for update transaction locks.
Follow up 3 curveball. What if an application uses optimistic locking with its version, but a raw SQL bulk update query bypasses Hibernate, leaving the at version field out of sync with entity states?
Answer. Bypassing Hibernate with raw SQL bulk updates does not increment the at version column automatically. Cached or loaded entities in the Hibernate first-level cache persistence context become stale. To fix, manually include version equals version +1 in the raw SQL query and execute entity manager .clear to refresh L1 cache.
Production Incident 79. A primary Postgres SQL database host experiences a hardware failure, triggering an automated failover to a standby replica. While the database failover completes in 10 seconds, 200 microservice pods simultaneously flood the new primary database with thousands of reconnect attempts, creating a connection storm that crashes the new primary database. As the on-call Java application support engineer, how do you resolve this connection storm?
Answer. When automated database failover triggers reconnect connection storms crashing the secondary master, my priority is to deploy database proxy connection poolers, configure client reconnect backoffs, and stabilize database connectivity using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check database server CPU and active connection metrics on the new primary database host during failover. 2. Inspect microservice application logs using kubectl logs for widespread database connection refused exceptions. 3. Confirm whether connection storm crashes impact the new primary database across all application clusters. Phase 2. Investigation and evidence gathering. 1. Review HikariCP connection pool failover settings across all microservice deployment manifests. 2. Check active database connection counts on the new primary host during failover max_connections limit breached. 3. Verify whether a database connection proxy such as AWS RDS proxy or PG bouncer was deployed between microservices and the database server. Phase 3. Root cause analysis. 1. Evidence collected. PostgreSQL logs on the new primary host showed fatal. Sorry, too many clients already with 6,000 connection attempts within 3 seconds. 2. Primary root cause. Reconnect connection storm. 200 microservice pods, each running 30 HikariCP connections, attempted to establish 6,000 simultaneous TCP connections to the new primary database immediately after failover without backoff or connection proxy, crashing the new database. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Temporarily scale application replicas down, stagger rolling restarts to avoid synchronized reconnects, and route traffic through an existing AWS RDS proxy or PG bouncer instance if available. 2. Permanent resolution. Configure application-level exponential reconnect backoff together with database proxy routing, AWS RDS proxy, or PG bouncer, so reconnect attempts are staggered during database failovers. 3. Validation. Confirm microservices connect cleanly to RDS proxy, new primary database CPU remains at 15% and application transactions resume. Phase 5. Recurrence prevention. 1. Mandate database proxy layers PG bouncer or AWS RDS proxy across all production microservice architectures. 2. Execute chaos engineering database failover drills and staging to validate connection storm resilience. 3. Configure HikariCP initialization, fail timeout, and max lifetime jitter settings across all base container images. Pro tip interview insight. When a primary database fails over, hundreds of application pods reconnect simultaneously, creating a connection storm that can crash the new primary database. Always deploy a connection pooling proxy like PG Bouncer or AWS RDS proxy to multiplex client connections and absorb reconnect spikes during failovers.
Follow-up 1 expected. A logical continuation of the incident. How does a database proxy like AWS RDS proxy or PG Bouncer protect databases from connection storms during failovers?
Answer. AWS RDS proxy or PG Bouncer maintains a small, fixed pool of persistent connections to the database host while multiplexing thousands of application client connections. During failovers, the proxy absorbs and queues incoming client reconnect spikes, presenting a controlled connection volume to the database.
Follow-up 2 deeper. Experience tester. What HikariCP parameters max lifetime, idle timeout, connection timeout should be tuned to handle database failover gracefully?
Answer. Set connection timeout equals 5005 seconds, so threads fail fast during failover rather than hanging. Set max lifetime equals 1,800,000 30 minutes with random variance, so connection retirements are spread out across pods over time, rather than closing simultaneously.
Follow-up 3 curveball. What if DNS caching in Java JVM network address.cache.ttl causes microservices to continue attempting connections to the old failed database IP address long after failover completes?
Answer. By default, older JVMs cache DNS lookups indefinitely. In modern Java and Kubernetes environments, explicitly configure network address.cache.ttl equals $30 java_home/conf/security/java.security. This forces the JVM to refresh DNS lookups every 30 seconds, resolving the new database IP address rapidly post-failover.
Category 5 Conclusion.
Mastering database query optimization, connection pool management, transactional boundaries, and distributed caching is what protects modern enterprise applications from connection storms, database deadlocks, and severe latency degradation. By setting explicit HikariCP leak thresholds, enforcing non-blocking schema indexes, applying read after write consistency, and implementing Spring Batch chunk-oriented streaming, you build an ultra-scalable, resilient data access architecture.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition from Category 5 Database, ORM, Cache and Batch to Category 6 REST APIs, Microservices and Serialization.
While building a high-performance database and caching layer guarantees data layer reliability, your distributed architecture will still fail if inter-service communication breaks. Cascading downstream latency, API gateway routing errors, circuit breaker trips, retry storms, MTLS certificate rotation failures, and Jackson serialization bugs can instantly paralyze a microservices ecosystem. We now transition from data persistence to distributed inter-service communication. Category 6. REST APIs, Microservices, and Serialization.
Category 6. REST APIs, Microservices and Serialization.
REST APIs, Microservices, and serialization scenarios govern how distributed HTTP services discover, authenticate, route, and communicate safely under heavy network loads. This category deep dives into resolving cascading downstream latency, resilience 4J circuit breaker trips, API gateway route mismatches, service discovery registry losses, thundering herd retry storms, distributed Saga compensation failures, Jackson infinite recursion, and open feign timeout mismatches. Mastering these scenarios ensures a fault-tolerant, loosely coupled microservices architecture.
Category 6. REST APIs, Microservices and Serialization 80 to 94.
Here are the 15 REST API, microservice, and serialization incidents we will solve in this category. Incident 80. Downstream service latency causes cascading Tomcat worker thread exhaustion. Incident 81. HTTP 500 error surge following microservice application deployment. Incident 82. Circuit breaker opens permanently blocking customer transactions. Incident 83. API gateway routing issues misdirect user traffic post-deployment. Incident 84. Eureka or console service discovery registry loss breaks inter-service calls. Incident 85. Retry storms overload downstream services during transient network blips. Incident 86. Authentication fails after MTLS certificate rotation across microservices. Incident 87. Saga distributed transaction failures leave data in inconsistent states. Incident 88. Jackson infinite recursion causes stack overflow error during serialization. Incident 89. Unknown JSON properties crash REST payload deserialization pipelines. Incident 90. Time zone serialization bugs corrupt customer transaction timestamps. Incident 91. Open feign timeout mismatch causes premature request terminations. Incident 92. REST client connection pool exhaustion stalls outgoing HTTP requests. Incident 93. API version mismatch breaks backward compatibility during deployments. Incident 94. Idempotency failures cause duplicate customer financial transactions. Total 15 REST API, microservice, and serialization incidents. Let's dive into Incident 80.
Production Incident 80. A core payment orchestration microservice experiences severe response time degradation. HTTP AP IP99 response latencies jump from 100 milliseconds to 15 seconds, causing client timeouts and cascading Tomcat worker thread exhaustion across upstream API gateways. As the on-call Java application support engineer, how do you resolve this cascading downstream latency?
Answer. When downstream service latency cascades upstream and exhausts caller Tomcat worker threads, my priority is to isolate slow dependencies using APM distributed tracing, configure tight I/O timeouts, and enforce circuit breaker bulkheads using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM distributed tracing Jaeger or Datadog to isolate which specific downstream dependency is introducing 15-second latency. 2. Check container CPU utilization in Grafana to verify if latency is caused by thread blocking or CPU starvation. 3. Confirm whether Tomcat worker thread exhaustion is triggering HTTP 503 errors at the upstream API gateway level. Phase 2. Investigation and evidence gathering. 1. Generate a thread dump using JCMD1 thread.print to analyze Tomcat worker thread states HTTP Neo 8080 exec. 2. Verify whether worker threads are stuck in socket input stream.socket read 0 waiting on untimed downstream HTTP socket reads. 3. Review downstream REST client configuration REST template, web client or OpenFane for connect and read timeout parameters. 4. Inspect resilience 4J circuit breaker metrics in Grafana to check if fallback mechanisms triggered. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed 180 Tomcat worker threads stuck in socket read 0 executing REST template.exchange. 2. Primary root cause. Missing downstream timeout and cascading latency. The payment service called an untimed downstream fraud detection API, causing Tomcat worker threads to block waiting for 15-second socket reads and cascading thread exhaustion upstream. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Reduce downstream request pressure by routing traffic to an existing fallback path or temporarily disabling the affected dependency. Then apply updated timeout or circuit breaker configuration and perform a rolling restart if required. 2. Permanent resolution. Configure explicit socket read timeouts read timeout equals 2000 milliseconds and refactor blocking calls to use non-blocking asynchronous web client executions. 3. Validation. Confirm worker threads clear from socket read 0, IP/IP99 latencies return to 100 milliseconds and 503 errors cease. Phase 5. Recurrence prevention. 1. Enforce resilience 4J circuit breakers and bulkhead thread isolation on all inter-service REST integrations. 2. Mandate explicit connect and read timeouts across all REST client bean auto configurations. 3. Conduct chaos engineering latency injection testing in staging to validate bulkhead isolation. Pro tip interview insight. Downstream microservice latency cascades upstream and exhausts caller thread pools. Always apply bulkhead isolation and circuit breakers like Resilience 4J with tight read timeouts on all downstream REST client calls, providing graceful fallback responses when a downstream dependency degrades.
Follow up when expected. A logical continuation of the incident. How does distributed tracing with correlation IDs, trace ID, and span ID isolate downstream microservice latency across distributed call chains?
Answer. Distributed tracing libraries like Spring Cloud Sleuth or Micrometer Tracing inject unique XB3 trace ID and XB3 span ID HTTP headers into every outgoing request. APM tools aggregate these spans into a unified trace timeline, showing the exact duration spent in each microservice and database call.
Follow up 2 deeper. Experienced tester. What is the difference between a circuit breaker resilience 4J and a bulkhead pattern when protecting microservices from downstream latency?
Answer. A circuit breaker monitors call failure rates and opens to fail fast when a downstream service degrades. A bulkhead isolates thread pool capacity per downstream service, for example, limiting fraud API calls to 20 threads, ensuring slow calls on one dependency cannot exhaust worker threads for unrelated endpoints.
Follow up 3 curveball. What if a downstream service returns HTTP 200 OK, but takes 10 seconds to stream response bytes? How does read timeout handle slow response streaming?
Answer. Read timeout socket timeout measures maximum idle time between consecutive TCP packets, not total request duration. If a slow downstream service sends 1 byte every second, read timeout will not trigger. To fix, Configure a higher-level request timeout or time limiter in Resilience 4J.
Production Incident 81. Immediately following a microservice release, API gateways report a massive surge in HTTP 500 internal server error responses, reaching a 45% error rate across customer transaction requests. As the on-call Java application support engineer, how do you resolve this HTTP 500 error surge?
Answer: when a new release triggers a surge in HTTP 500 errors due to unhandled runtime exceptions, my priority is to inspect exception stack traces, execute a fast rollback to restore traffic, and implement global exception handlers using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check Grafana HTTP status metrics to confirm a 45% error rate spike on HTTP 500 internal server error responses. 2. Verify whether 500 errors impact all microservice endpoints or specific API routes introduced in the deployment. 3. Check Splunk or ELK logs to capture unhandled runtime exception. Stack traces from newly deployed pods. Phase 2. Investigation and evidence gathering. 1. Inspect application logs using kubectl logs for unhandled null pointer exception or response status exception traces. 2. Review recent code commit diffs in controller and service layers for unchecked optional fields. 3. Check whether Spring MVC or WebFlux global exception handlers at controller advice catch and format runtime exceptions. Phase 3. Root cause analysis. 1. Evidence collected. Splunk logs showed java.lang.null pointer exception inside user address formatter .format called by order controller. 2. Primary root cause. Unhandled runtime exception. A newly deployed address formatting method failed to handle null optional fields, throwing unhandled null pointer exceptions that bypassed controller logic and returned generic HTTP 500 errors to clients. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Perform an immediate rolling rollback using kubectl rollout undo to restore the previous stable release artifact and clear the HTTP 500 error surge. 2. Permanent resolution. Fix the underlying null handling defect using defensive validation, optional handling where appropriate, and implement at controller advice to standardize RFC 7807 problem details responses. 3. Validation. Redeploy hotfix, confirm HTTP 500 error rates drop to 0% and verify transaction processing health. Phase 5. Recurrence prevention. 1. Mandate at controller advice global exception, handling returning RFC 7807 problem details across all microservices. 2. Enforce 90% unit and integration test branch coverage in CI and CD pipelines. 3. Configure automated canary deployment error rate gates in Argo rollouts. Pro tip interview insight. A sudden HTTP 500 surge post-deployment indicates unhandled runtime exceptions bypassing controller logic. Always implement a global at controller advice exception handler in Spring MVC or WebFlux to catch unhandled exceptions. Log diagnostic context and return structured RFC 7807 problem details to clients.
Follow up when expected. A logical continuation of the incident. How does Spring's at controller advice and at exception handler standardize error responses across microservices using RFC 7807 problem details?
Answer: at controller advice defines a global interceptor for exceptions thrown across all controllers. Combined with at exception handler, it catches specific exceptions like null pointer exception and converts them into standardized RFC 7807 JSON error payloads containing type, title, status, and detail fields.
Follow up 2 deeper. Experienced tester. Why should microservices avoid exposing raw Java stack traces in HTTP 500 response bodies in production?
Answer: exposing raw Java stack traces in HTTP response bodies leaks internal class names, library versions, database table names and framework paths to unauthenticated callers, creating severe security reconnaissance vulnerabilities for attackers.
Follow up 3 curveball. What if an HTTP 500 error surge is caused by an unhandled database transaction rollback rather than application logic null pointers?
Answer: if an unhandled database constraint violation occurs inside a Spring at transactional method, Spring's transaction manager marks the transaction as rollback only and rethrows data integrity violation exception. If unhandled by a controller advice, it bubbles up as an HTTP 500 error.
Production Incident 82. A high-throughput order microservice trips its Resilience 4J circuit breaker to open state. All subsequent order creation requests fail instantly with call not permitted exception, blocking customer checkout transactions even after the downstream inventory service has recovered. As the on-call Java application support engineer, how do you resolve this circuit breaker lockup?
Answer: when a circuit breaker remains stuck in open state blocking transactions after downstream recovery, my priority is to inspect state transition configurations, force a _open state transition via actuator, and tune failure evaluation windows using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM metrics for Resilience 4J circuit breaker state transitions close to open. 2. Check application error logs using kubectl logs for io.github.resilience 4j.circuitbreaker.call not permitted exception. 3. Confirm whether checkout transaction failures impact all order creation attempts or specific downstream endpoints. Phase 2. Investigation and evidence gathering. 1. Inspect Resilience 4J configuration properties in application.yml sliding window size, failure rate threshold, wait duration in open state. 2. Check whether automatic transition from open to half open enabled is set to true or false. 3. Query actuator circuit breaker metrics via /actuator/circuit breakers or /actuator/metrics/resilience 4j.circuitbreaker.state. Phase 3. Root cause analysis. 1. Evidence collected. Actuator health endpoint showed inventory service circuit breaker in state open with automatic transition from open to half open. Enabled equals false and wait duration in open state equals 30 minutes. 2. Primary root cause. Misconfigured circuit breaker state transition. The circuit breaker was configured with automatic transition disabled and an excessive 30-minute open wait duration, keeping the circuit permanently open long after downstream inventory recovered. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Transition the circuit breaker state to /open via actuator post endpoint /actuator/circuit breakers /inventory service /state, where operationally enabled, allowing trial requests to pass and restore traffic immediately. 2. Permanent resolution. Configure automatic transition from open to half open. Enabled equals true and reduce wait duration in open state equals 10 seconds in application.yml. 3. Validation. Confirm circuit breaker state transitions from /open to closed and verify customer checkout success rates reach 100%. Phase 5. Recurrence prevention. 1. Standardize Resilience 4J circuit breaker configurations across all microservices using central archetype templates. 2. Configure Prometheus alerts on circuit breaker open state transitions lasting longer than 1 minute. 3. Conduct chaos engineering tests simulating downstream failure and recovery in staging. Pro tip interview insight. Circuit breakers prevent cascading failures by failing fast when a dependency degrades. However, always enable automatic transition from open to /open automatic transition from open to half open. Enabled equals true, and set a short open wait duration, for example 10 seconds, so the circuit automatically tests downstream recovery and restores normal traffic flow.
Follow up when expected. A logical continuation of the incident. What are the 3 core states of a Resilience 4J circuit breaker closed, open, half_open, and how do sliding windows evaluate failure thresholds?
Answer: in closed state, all requests pass. If failure rates exceed failure rate threshold within a sliding window count_based or time_based, the circuit transitions to open, instantly failing all requests. After wait duration in open state, it transitions to half_open, allowing a limited number of trial requests to test downstream recovery.
Follow up 2 deeper. Experienced tester. How does a resilience 4J fallback method provide graceful degradation when a circuit breaker enters open state?
Answer: a fallback method annotated via at circuit breaker with name equals service. Fallback method equals get fallback catalog executes automatically when the circuit is open or throws call not permitted exception. It returns cached, default, or degraded data such as static recommendations to the user without calling the broken downstream API.
Follow up 3 curveball. What if a circuit breaker transitions to half_open and sends 10 trial requests, but all 10 trial requests fail, reopening the circuit? How do you prevent infinite half_open or open oscillation?
Answer: if downstream dependencies remain broken, reopening the circuit is correct behavior. However, to prevent oscillation storms, configure exponential backoff on wait duration in open state using Resilience 4J's interval function, increasing the open wait duration on consecutive half_open failures.
Production Incident 83. Following a Canary release switch, Spring Cloud Gateway, or Nginx API Gateway, routes 100% of user traffic to legacy V1 microservice pods, instead of splitting traffic or routing to newly deployed V2 pods. Users are unable to access newly deployed features. As the on-call Java application support engineer, how do you resolve this API gateway routing issue?
Answer: when an API gateway fails to route traffic to newly deployed microservice pods, my priority is to inspect gateway route predicates, verify Kubernetes pod label selectors, and update route definitions using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect API gateway routing metrics in Grafana to confirm 100% of user traffic is directed to version equals V1 target pods. 2. Check gateway access logs to verify whether request path predicates or header matchers are evaluating correctly. 3. Confirm whether routing misdirection impacts all API routes or specific Canary feature paths. Phase 2. Investigation and evidence gathering. 1. Query active gateway route definitions via actuator/gateway/gateway/routes or Nginx ingress configurations. 2. Check Kubernetes service target selectors and pod labels using kubectl get pods-show labels. 3. Inspect deployment manifests for label discrepancies between gateway route predicates version equals V2 and actual pod labels version equals 2. Phase 3. Root cause analysis. 1. Evidence collected. Actuator/gateway/routes showed route predicate searching for pod label version equals V2, but kubectl get pods-show labels showed V2 pods labeled with version equals 2. 2. Primary root cause. Label selector mismatch. A deployment manifest error labeled V2 pods with version equals 2 missing the V prefix, causing the API gateway target group selector to ignore V2 pods and route 100% of traffic to V1 pods. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Relabel V2 pods using kubectl label pod-lapp equals payments version equals V2-overwrite or update deployment manifests via Helm, restoring correct gateway routing immediately. 2. Permanent resolution. Standardize Kubernetes pod label and gateway route predicate naming conventions across all Helm chart templates. 3. Validation. Confirm/actuator/gateway/routes discovers V2 pod endpoints and verify traffic splits 50-50 between V1 and V2. Phase 5. Recurrence prevention. 1. Implement automated pre-deployment manifest linter assertions in CI and CD pipelines to validate label selector alignment. 2. Configure automated Canary deployment route verification in Argo rollouts prior to opening traffic gates. 3. Audit GitOps release repositories to enforce strict label naming standards. Pro tip interview insight. API gateway routing failures post-deployment are frequently caused by subtle label selector mismatches between gateway route predicates and Kubernetes pod labels. Always inspect gateway route definitions via /actuator/gateway/routes to verify active target endpoint registrations.
Follow up when expected. A logical continuation of the incident. How does Spring Cloud Gateway evaluate route predicates and gateway filters for incoming HTTP requests?
Answer: Spring Cloud Gateway matches incoming HTTP requests against configured route predicates like path, method, or header. When a predicate matches, gateway filters process the request, for example, modifying headers or stripping prefixes before forwarding the request to the target URI.
Follow up deeper. Experienced tester. What is the difference between path-based routing /API/v1/orders and header-based routing XAPI version v2 in API gateways?
Answer: Path-based routing uses URI path segments to route requests to specific service clusters. Header-based routing inspects HTTP header attributes like XAPI version v2 to route traffic dynamically to specific canary or A or B testing pod subsets without altering public URL structures.
Follow up 3 curveball. What if an API gateway route strip prefix filter strip prefix equals 1 strips 1 path segment too many, forwarding invalid URI/orders instead of /API/orders to downstream microservices and returning HTTP 404?
Answer: This occurs when strip prefix equals 1 strip /API from /API/v1/orders, forwarding /v1/orders when the downstream controller expects /API/v1/orders. To fix, adjust strip prefix equals 0 or use rewrite path equals /API/open (segment star close $, curly brace segment close curly brace. Precise rejects URI rewriting.
Production Incident 84. A Spring Cloud microservice architecture experiences total inter-service communication failure. Microservices fail to discover each other, throwing illegal state exception, no instances available for payment service when invoking OpenFain or REST template calls. As the on-call Java application support engineer, how do you resolve this service discovery registry loss?
Answer: When service discovery registry loss breaks inter-service routing, my priority is to inspect Eureka or console cluster health, force client re-registration via actuator, and evaluate migration to Kubernetes native DNS service discovery using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect microservice error logs using kubectl logs for illegal state exception, no instances available for payment service. 2. Check Netflix Eureka or console server management dashboard to verify active registered service instance counts. 3. Confirm whether inter-service discovery failures impact all microservice calls or specific service clusters. Phase 2. Investigation and evidence gathering. 1. Inspect Eureka server logs for emergency Eureka may be incorrectly claiming instances are up when they are not self-preservation mode. 2. Verify network connectivity between client microservices and Eureka server endpoints using kubectl exec with curl. 3. Review client heartbeat configuration properties in application.yml eureka.instance.lease renewal interval in seconds. Phase 3. Root cause analysis. 1. Evidence collected. Eureka dashboard showed self-preservation mode triggered with 0 active instances registered for payment service. 2. Primary root cause. Eureka self-preservation trigger. A transient network partition interrupted client heartbeats, causing Eureka server to enter self-preservation mode, freeze registry updates, and drop active pod IP registrations. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR, Restore connectivity between clients and Eureka. Force client re-registration using /actuator/service registry. And restart affected Eureka nodes only if registry recovery fails. 2. Permanent resolution. Deploy Eureka server in a multi-region active-active cluster or migrate inter-service discovery to Kubernetes native DNS service discovery. 3. Validation. Confirm Eureka dashboard shows all microservice instances registered up and open feign inter-service calls succeed. Phase 5. Recurrence prevention. 1. Migrate inter-service communication to Kubernetes native DNS service discovery Spring Cloud Starter Kubernetes client. 2. Configure high-availability multi-replica Eureka or console server deployments across availability zones. 3. Set Prometheus alerts for Eureka client, lease renewal drops, and unregistered service counts. Pro tip interview insight. Eureka self-preservation mode triggers when network glitches prevent client heartbeats, causing Eureka to stop evicting dead instances. For Kubernetes deployments, prefer native K8's DNS service discovery over Eureka or console to simplify architecture and eliminate external service registry failure points.
Follow-up 1 expected. A logical continuation of the incident. How does Eureka self-preservation mode work, and why can it serve stale IP addresses to microservices during network partitions?
Answer: Eureka monitors client heartbeats. If more than 15% of heartbeats fail within a minute, for example, due to a network partition, Eureka assumes the network is broken rather than all instances dying. It enters self-preservation mode, pausing instance evictions to protect registry state, which can serve stale IPs.
Follow-up 2 deeper. Experience tester. What is the fundamental architectural difference between client-side service discovery, Eureka plus feign, and server-side service discovery, Kubernetes, DNS plus kube proxy?
Answer: in client-side discovery Eureka, the client queries Eureka for instance IPs, caches the registry locally, and load balances requests itself. In server-side discovery Kubernetes, the client sends requests to a virtual service DNS name, for example payment service, and kube proxy or core DNS load balances traffic at the infrastructure level.
Follow-up 3 curveball. What if a microservice pod re-registers with Eureka under a new IP address after pod restart, but client-side DNS or feign connection pool caching continues sending requests to the old dead IP address?
Answer: this occurs when open feigns underlying HTTP client like Ribbon or Apache HTTP client caches stale DNS lookups or keeps idle TCP connections open to dead IPs. To fix, configure Spring Cloud Load Balancer to refresh service instances promptly or reduce service instance cache TTL where caching is enabled, and set JVMD NSTTL network address .cache.ttl equals 5 to force rapid cache invalidation.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 85. An external payment gateway experiences a brief 2-second database slowdown. Immediately, 500 calling microservice pods trigger unbounded automated retries, sending 50,000 requests per second to the payment gateway, crashing it completely, and causing an extended P1 outage. As the on-call Java application support engineer, how do you resolve this retry storm?
Answer. When unbounded retries amplify minor latency, blips into a self-inflicted retry amplification storm. My priority is to disable retries immediately, enforce exponential backoff with randomized jitter, and apply retry budgets using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM request volume metrics on the downstream payment gateway to confirm a 50,000 RPS spike during latency windows. 2. Check caller application logs using kubectl logs to verify rapid retry execution loops across pod replicas. 3. Confirm whether the retry storm outage impacts all payment operations or specific checkout workflows. Phase 2. Investigation and evidence gathering. 1. Review Resilience 4J or Spring retry configuration properties in client application.yml max attempts, wait duration, exponential backoff. 2. Check whether retries were configured with fixed short wait intervals, for example wait duration equals 10 milliseconds without randomized jitter. 3. Inspect API gateway rate limiting metrics on downstream endpoints. Phase 3. Root cause analysis. 1. Evidence collected. Client logs showed 500 pods retrying failed requests 5 times at fixed 10 milliseconds intervals, generating 50,000 RPS. 2. Primary root cause. Retry storm thundering herd retries. Calling microservices configured fixed short retries without exponential backoff or randomized jitter, amplifying a minor 2-second database latency blip into a self-inflicted 50,000 RPS retry amplification storm. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Temporarily disable retries across client microservices via config map update or apply API gateway rate limiting. Then perform a rolling restart to let the payment gateway recover. 2. Permanent resolution. Configure Resilience 4J retry with exponential backoff and randomized jitter multiplier equals 2.0. Randomized weight factor equals 0.5. 3. Validation. Confirm request volume to payment gateway drops from 50,000 RPS to baseline 1,000 RPS and verify payment success. Phase 5. Recurrence prevention. 1. Implement retry budgets in Service Mesh Istio or Resilience 4J, capping retries to a maximum 10% of total cluster traffic. 2. Mandate exponential backoff with randomized jitter on all REST client configurations across microservices. 3. Prohibit automatic retries on non-idempotent HTTP methods, such as POST, without explicit idempotency tracking. Pro tip: interview insight. Retry storms occur when hundreds of caller instances retry failed requests simultaneously at fixed intervals, magnifying minor latency blips into massive self-inflicted retry storms. Always combine retries with exponential backoff and randomized jitter, and cap retries using a retry budget.
Follow up when expected. A logical continuation of the incident. How does adding randomized jitter to exponential backoff algorithms break synchronized retry storms across microservice clusters?
Answer: exponential backoff increases wait duration between retries 1 second, 2 seconds, 4 seconds, 8 seconds. Adding randomized jitter, for example, plus or minus 50% random variation, desynchronizes retry timing across 500 caller pods, spreading retry requests evenly over time, instead of hitting the downstream server in synchronized burst waves.
Follow up 2 deeper. Experienced tester. What is a retry budget in Istio or Resilience 4J, and how does it prevent cascading retry storms from consuming cluster capacity?
Answer: a retry budget tracks the ratio of retries to initial requests across a service pool. If retries exceed a configured threshold, for example, max 10% of total requests, the retry budget rejects further retry attempts instantly, preventing cascading retry amplification during downstream outages.
Follow up 3 curveball. Why should non-idempotent HTTP requests like POST never be retried automatically without explicit idempotency key tracking?
Answer: if a POST request such as charging a credit card reaches the server and executes successfully, but the HTTP response times out on the network, an untracked retry will submit a second POST request, creating a duplicate payment charge and corrupting business data.
Production Incident 86. Following a scheduled mutual TLS/MT/LS certificate rotation on an internal API gateway, all inter-service microservice communications fail with SSL handshake exception. PKI path building failed. sun.security.provider.certpath.sun cert path builder exception. As the on-call Java application support engineer, how do you resolve this MTLS rotation outage?
Answer: when an MTLS certificate rotation triggers SSL handshake exceptions across microservices, my priority is to inspect Java Trust Store CA cert bundles, update container trust stores, and restore TLS handshakes using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application logs across client microservices using kubectl logs for javax.net.ssl.ssl handshake exception. 2. Check inter-service communication metrics in Istio or Linkerd service mesh to verify MTLS handshake failure rates. 3. Confirm whether SSL handshake failures impact all inter-service REST calls or specific API gateway routes. Phase 2, Investigation and Evidence Gathering. 1. Inspect client Java Trust Store casserts inside running containers using key tool -list -keystore $java_home/lib/security/casserts. 2. Test TLS handshake and certificate chain presentation using OpenSSLS_client-connect API gateway :8443-show certs. 3. Verify whether the newly rotated server intermediate CA certificate exists in the client microservice Java Trust Store. Phase 3. Root cause analysis. 1. Evidence collected. OpenSSL output showed API gateway presenting a new intermediate CA certificate, while client container casserts listed only the expired root CA alias. 2. Primary root cause. Missing intermediate CA in Java Trust Store. The certificate rotation updated the server-side TLS certificate, but the corresponding new intermediate CA certificate was omitted from the client microservice Java Trust Store casserts, breaking PKIX certificate chain validation. Phase 4. Resolution and Service Restoration. 1. Immediate recovery reduce MTTR. Mount the updated Trust Store or CA bundle into client pods via Kubernetes secret volume mount, and pass -d javax.net.ssl.truststore =/etc/ssl/certs/truststore.jks and JVM startup flags, then perform a rolling restart. 2. Permanent resolution. Rebuild base Docker images with automated CA certificate trust bundle synchronization, ensuring all client containers trust the new CA. 3. Validation. Confirm SSL handshake exception errors drop to 0, verify inter-service MTLS calls succeed, and monitor traffic health. Phase 5. Recurrence prevention. 1. Automate MTLS certificate and trust store management using Cert Manager in Kubernetes. 2. Enforce dual trust store transition windows trusting both old and new CA certificates simultaneously during certificate rotations. 3. Implement automated TLS handshake validation integration tests in CI and CD pipelines prior to certificate cutover. Pro tip interview insight. SSL handshake exception with PKIX path building failed means the client JVM Trust Store casserts does not trust the certificate chain presented by the server. During certificate rotations, always deploy the new CA certificate to client trust stores before activating the new server certificate to prevent MTLS outages.
Follow up when expected. A logical continuation of the incident. How do you use the OpenSSL command? OpenSSLS_client- connect host port -show certs to debug MTLS certificate chain validation failures.
Answer. OpenSSLS_client initiates a raw TLS handshake with the target server, printing every certificate presented in the server certificate chain. By inspecting the subject and issuer strings of each certificate, you can pinpoint missing intermediate CAs or untrusted root certificates causing client handshake failures.
Follow up 2 deeper. Experience tester. What is the precise architectural difference between a key store and a trust store in Java SSL or TLS configuration?
Answer. A key store stores private keys and public certificates used by the local application to prove its own identity to remote callers during MTLS handshakes. A trust store stores trusted certificate authority (CA) public certificates used by the application to verify the identity of remote servers.
Follow up 3 curveball. How does Kubernetes Cert Manager automate zero downtime MTLS certificate rotation across microservice pods in Istio or Linkerd?
Answer. Cert Manager manages certificate CRDs, automatically requesting and renewing TLS certificates before expiration. In service meshes like Istio, the Envoy sidecar proxy dynamically reloads renewed secret certificates from mounted volumes without restarting the main application container, enabling zero downtime MTLS rotation.
Production Incident 87. A distributed order creation saga spanning order, payment, and inventory microservices fails midway when payment succeeds, but inventory reservation fails due to an out-of-stock condition. However, the compensating transaction fails to trigger, leaving customer credit cards charged without creating orders. As the on-call Java application support engineer, how do you resolve this saga failure?
Answer: when a distributed saga step fails without triggering compensating transactions, my priority is to inspect saga event topics or streams, execute manual compensating refunds, and enforce state machine event handling using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Trace distributed transaction state across Kafka or RabbitMQ Saga event topics or APM distributed tracing. 2. Compare payment and inventory database tables to identify order IDs where payment succeeded but inventory reservation failed. 3. Confirm whether compensating transaction failures affect all out-of-stock orders or specific message consumer groups. Phase 2. Investigation and evidence gathering. 1. Inspect Saga Orchestrator or Choreography event listener logs at Kafka Listener for missing event consumer bindings. 2. Check Message Broker Dead Letter Topics DLT for unhandled inventory failed event messages. 3. Review compensating transaction implementation logic in payment service. Refund payment for unhandled exceptions. Phase 3. Root cause analysis. 1. Evidence collected. Kafka consumer logs showed inventory failed event published to topic inventory events, but order Saga Orchestrator consumer group binding was omitted. 2. Primary root cause. Unhandled compensation event binding. The inventory service published an inventory failed event, but the order Saga Orchestrator lacked an active consumer binding for that topic, skipping the execution of refund payment command and leaving data inconsistent. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Verify compensation has not already completed. Then manually trigger idempotent refund API calls via admin CLI script for affected order IDs, and deploy an emergency fix, adding the missing Kafka consumer event binding. 2. Permanent resolution. Refactor Saga implementation to use a persistent state machine-backed Saga orchestrator such as Axon or Temporal with idempotent compensating commands. 3. Validation. Replay failed inventory events, confirm payment refunds, execute and verify end-to-end Saga data consistency. Phase 5. Recurrence prevention. 1. Mandate persistent state machine-backed Saga orchestrators for all multi-service distributed transaction workflows. 2. Enforce strict idempotency on all compensating transaction commands across microservices. 3. Implement automated end-to-end Saga failure and compensation integration tests in CI and CD pipelines. Pro tip: interview insight. In microservices, distributed transactions use the Saga pattern instead of 2PC. If a step fails, compensating transactions, for example refund payment, must execute to undo previous steps. Always make compensating transactions idempotent and persist Saga execution state, so compensation retries until consistency is restored.
Follow up when expected. A logical continuation of the incident. What is the difference between orchestration-based sagas and choreography-based sagas in event-driven microservices?
Answer: in orchestration sagas, a centralized coordinator Saga orchestrator explicitly directs participant microservices by sending command messages and managing execution state. In choreography sagas, participant microservices listen to domain events independently and trigger local transactions or compensating events without a central coordinator.
Follow up 2 deeper. Experienced tester. Why must compensating transactions in a saga pattern be designed to be completely idempotent and retriable?
Answer: network blips or temporary downstream outages can cause compensating commands like refund payment to fail or time out. To guarantee eventual consistency across microservices, the Saga orchestrator will retry compensating commands until they succeed. Idempotency guarantees that executing a refund 5 times produces the exact same result as executing it once.
Follow up 3 curveball. What if a compensating transaction in a saga fails permanently? For example, a customer credit card account is closed before a refund executes. How do you handle uncompensatable saga failures?
Answer: when an automated compensating transaction encounters a non-retrievable business failure, the saga orchestrator routes the failed transaction to an explicit human in the loop HITL administrative queue or dead letter queue. An operator or financial system then manually resolves the account credit out of band.
Production Incident 88. A newly deployed REST endpoint returning order details crashes during JSON serialization with java.lang.stack overflow error. The worker thread exhausts its stack memory, returning HTTP 500 responses to callers whenever order entities with parent-child relationships are requested. As the on-call Java application support engineer, how do you resolve this Jackson serialization recursion?
Answer: when bidirectional JPA entity relationships trigger infinite Jackson serialization recursion, my priority is to break the object reference loop, isolate DTO transformation layers, and restore endpoint health using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect application error logs using kubectl logs to confirm java.lang.stack overflow error originating from Jackson Object Mapper. 2. Verify whether Stack Overflow error crashes occur on all API endpoints or specific entity retrieval routes. 3. Confirm whether HTTP 500 error responses trigger API gateway circuit breaker trips. Phase 2. Investigation and evidence gathering. 1. Inspect JPA entity models, order entity and order item entity for bidirectional at one-to-many and at many-to-one relationship mappings. 2. Review Jackson annotations on parent and child entity fields for missing at JSON managed reference, at JSON back reference, or at JSON ignore. 3. Check recent REST controller changes to verify if raw JPA entity objects are being returned directly in HTTP response bodies. Phase 3. Root cause analysis. 1. Evidence collected. Stack trace showed thousands of repeating calls between order entity.getItems and order item entity.getOrder. 2. Primary root cause. Infinite Jackson serialization recursion. Jackson attempted to serialize a bidirectional parent-child JPA relationship order-to-order item to order-to-order item, triggering an infinite recursion loop that exhausted JVM thread stack memory. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Annotate parent-child entity fields with at JSON managed reference and at JSON back reference, rebuild artifact, and perform a rolling deployment. 2. Permanent resolution. Refactor REST controllers to transform raw JPA entities into dedicated, flat REST DTO objects before returning HTTP responses. 3. Validation. Confirm zero Stack Overflow error exceptions, verify order JSON payloads serialize cleanly, and confirm HTTP 200 OK responses. Phase 5. Recurrence prevention. 1. Enforce architectural DTO transformation layers between JPA persistence models and REST API response payloads across all microservices. 2. Add automated Jackson serialization unit tests in CI and CD pipelines to validate entity payload serialization. 3. Implement static code analysis rules Sonar Cube flagging raw JPA entities returned from at-rest controller methods. Pro tip interview insight. Never return raw JPA entities directly from Spring REST controllers. Bidirectional entity relationships at one-to-many or at many-to-one cause infinite Jackson serialization, loop stack overflow error. Always map JPA entities to dedicated REST DTOs or use at JSON managed reference and at JSON back reference annotations.
Follow up when expected. A logical continuation of the incident. How do at JSON managed reference and at JSON back reference work together to break infinite Jackson serialization loops in bidirectional Java object graphs?
Answer: at JSON, managed reference is placed on the parent reference and tells Jackson to serialize the child objects normally. At JSON, back reference is placed on the child's back reference to the parent, instructing Jackson to omit the parent reference during serialization, breaking the loop.
Follow up 2 deeper. Experience tester. How does at JSON identity info solve circular object reference serialization compared to at JSON ignore?
Answer: at JSON, ignore completely excludes a property from serialization, losing that relationship data. At JSON, identity info with generator equals object ID generators dot property generator dot class. Property equals ID serializes the full object on its first occurrence and replaces subsequent circular references with the object's ID, preserving graph structure.
Follow up 3 curveball. What if an entity uses Jackson's object mapper to serialize a self-referential graph like an organizational hierarchy tree, and at JSON, ignore removes needed child node fields?
Answer: for self-referential tree structures, where nodes contain lists of child nodes, use at JSON identity info, or create a specialized tree DTO class that recursively maps child nodes without referencing back to parents, avoiding infinite recursion while retaining full hierarchy data.
Production Incident 89. An upstream microservice deploys a new release adding a new discount code field to its JSON payload. Immediately, the downstream consumer service crashes during payload processing, throwing com.fasterxml.jackson.databind.exe. Unrecognized property exception, unrecognized field discount code. As the on-call Java application support engineer, how do you resolve this deserialization outage?
Answer: when an upstream JSON schema addition breaks downstream consumer deserialization, my priority is to configure lenient Jackson matching, deploy ignore unknown annotations, and restore message processing using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check consumer microservice error logs using kubectl logs for unrecognized property exception. 2. Verify whether JSON deserialization failures impact all incoming REST requests or specific consumer endpoints. 3. Confirm which upstream microservice release introduced the new undeclared JSON field. Phase 2. Investigation and evidence gathering. 1. Review consumer DTO class definitions for missing at JSON ignore properties with ignore unknown equals true annotations. 2. Inspect consumer application.yml for Jackson deserialization property, setting spring.jackson.deserialization.fail on unknown properties. 3. Examine raw incoming JSON payloads from the upstream service to verify the exact name and data type of the new field. Phase 3. Root cause analysis. 1. Evidence collected. Consumer logs showed unrecognized property exception. Unrecognized field discount code class com.example.order DTO not marked as ignorable. 2. Primary root cause. Strict Jackson deserialization default. The consumer's Jackson object mapper was configured with default strict matching fail underscore on underscore unknown underscore properties equals true, causing deserialization to crash when upstream added a new, undeclared JSON property. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Annotate consumer DTO classes with at JSON. Ignore properties with ignore unknown equals true, or set spring.jackson.deserialization.fail on unknown properties equals false in config map, and perform a rolling deployment. 2. Permanent resolution. Enforce global lenient Jackson deserialization configurations across all microservice consumers. 3. Validation. Confirm unrecognized property exception errors cease. Consumer REST endpoints process payloads cleanly and transaction health normalizes. Phase 5. Recurrence prevention. 1. Mandate at JSON ignore properties with ignore unknown equals true on all consumer DTO classes across microservices. 2. Configure global Jackson object mapper customization. Bean setting fail underscore on underscore unknown underscore properties to false in base starters. 3. Implement consumer-driven contract testing in CI and CD pipelines to validate schema evolution tolerance. Pro tip interview insight. Downstream microservices must tolerate upstream API schema evolution. By default, Jackson throws unrecognized property exception on new unknown fields. Always set spring.jackson.deserialization.fail on unknown properties equals false, or annotate DTOs with @JSON. Ignore properties with ignore unknown equals true to ensure resilient, forward compatible deserialization.
Follow up when expected. A logical continuation of the incident. How does setting deserialization feature .fail on unknown properties to false ensure forward compatibility in REST API integrations?
Answer. When fail underscore on underscore unknown underscore properties is false, Jackson silently ignores any new or unexpected JSON fields present in incoming payloads that are not mapped in the consumer's Java DTO class. This allows upstream services to add new fields without breaking existing downstream consumers.
Follow up 2 deeper. Experience tester. What is the difference between class level @JSON, ignore properties with ignore unknown equals true, and global object mapper customization in Spring Boot?
Answer. @JSON, ignore properties with ignore unknown equals true applies lenient deserialization locally to a specific DTO class. Global object mapper configuration spring.jackson.deserialization.fail on unknown properties equals false applies lenient matching universally across all REST endpoints and message listeners in the microservice.
Follow up 3 curveball. What if an upstream API changes a field's data type, for example, string to integer array rather than adding a new field? How do you handle breaking JSON data type changes safely?
Answer. Changing a field's data type breaks existing deserializers. To handle safely, the upstream service must implement API versioning, for example /v2/orders, or a new field discount codes list, or write a custom Jackson JSON deserializer that accepts both legacy string formats and new integer array formats during a transition window.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire master vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Production Incident 90. A global financial transaction service records payment timestamps in UTC. However, post-deployment, European customers report that payment execution timestamps on invoices are displayed 5 hours in the past, corrupting accounting audit trails. As the on-call Java application support engineer, how do you resolve this time zone serialization bug?
Answer. When time zone serialization converts UTC timestamps to local container server times causing data corruption, my priority is to enforce UTC Jackson date formatting, standardize ISO 8601 string representations, and set container JVM system time using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Compare raw database UTC timestamps, select created _ at from transactions against JSON API responses. 2. Check application container environment variables using kubectl exec to verify system time zone settings. 3. Confirm whether timestamp corruption impacts all global customer portals or specific regional zones. Phase 2. Investigation and evidence gathering. 1. Inspect Jackson object mapper date serialization properties in application.yml spring.jackson.timezone and spring.jackson.serialization.write dates as timestamps. 2. Review Java entity and DTO date field types java.util.date versus Java 8 instant or offset date time. 3. Check whether Jackson serializes dates as raw numeric epoch milliseconds without time zone offset indicators. Phase 3. Root cause analysis. 1. Evidence collected. API returned numeric epoch timestamp 1711 zeros without offset, which client browsers parsed using local system time instead of UTC. 2. Primary root cause. Default local time zone serialization. Jackson was configured with write_dates_ as _timestamps equals true and defaulted to the local container OS time zone America or new_York, stripping ISO 8601 UTC offset specifiers during JSON serialization. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Configure spring.jackson.timezone equals UTC and spring.jackson.serialization.write dates as timestamps equals false in config map, and perform a rolling deployment. 2. Permanent resolution. Use ISO 8601 formatted UTC strings at JSON format with shape equals JSON format dot shape dot string. Pattern equals YYYY-MM-DDTHH colon MM colon SS dot SSSZ. Time zone equals UTC and Java 8 instant fields across all DTOs. 3. Validation. Verify API responses return ISO 8601 strings ending in Z. For example, August 1, 2026 T 1030.0000Z, and confirm invoice timestamps display accurately globally. Phase 5. Recurrence prevention. 1. Enforce Java 8 date or time API instant. Offset date time over legacy java.util.date across all repositories. 2. Set JVM system property -d user.timezone equals UTC in base container Docker files. 3. Add automated integration tests asserting ISO 8601 UTC date formats in API response contracts. Pro tip interview insight. Never rely on JVM default time zones. For REST API date serialization, always configure Jackson to serialize dates as ISO 8601. Formatted UTC strings spring.jackson.serialization.write dates as timestamps equals false and spring.jackson.timezone equals UTC, and use Java instant or offset date time types.
Follow up when expected. A logical continuation of the incident. Why is Java 8 instant or offset date time preferred over java.util.date and java.util.calendar for microservice API DTOs?
Answer: java.util.date is mutable, not thread safe, and carries no built-in time zone context relying on JVM default time zone. Java 8 instant represents an unambiguous point on the UTC timeline, while offset date time includes explicit UTC offset information, making date serialization predictable.
Follow up 2 deeper. Experience tester. How does ISO 8601 date time, string formatting, YYYY-MM-DDTHH colon, MM colon SS.SSS, Z eliminate time zone ambiguity across cross-border REST clients?
Answer: ISO 8601 incorporates explicit UTC offset designators like Z for 0 offset or +05:30. When a cross-border client receives an ISO 8601 string, its local date time parser unambiguously calculates local display time relative to UTC regardless of client device location.
Follow up 3 curveball. What if a database driver converts Postgres SQL timestamp with time zone into container local time zone before handing the entity to Hibernate? How do you force JDBC drivers to communicate in UTC?
Answer: configure Hibernate to use UTC by setting hibernate.jdbc.timezone equals UTC, or Spring Boot property spring.jpa.properties.hibernate.jdbc.timezone equals UTC. Keep the database storing timestamps in UTC and configure the JVM and Jackson to serialize UTC consistently. This ensures Hibernate reads and writes timestamp values in UTC regardless of the container's local operating system time zone.
Production Incident 91. An open Feign client invoking an internal inventory microservice fails with Feign.retriable exception. Read timed out after 1 second. Even though the underlying HTTP client and Resilience 4J circuit breaker were configured with a 5-second read timeout. As the on-call Java application support engineer, how do you resolve this timeout mismatch?
Answer: when OpenFeign built-in timeouts override underlying HTTP client and circuit breaker settings, causing premature request failures, my priority is to inspect Feign configuration hierarchies, align socket timeouts, and restore call stability using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect client application error logs using kubectl logs for feign.retrievable exception. Read timed out. 2. Compare response time metrics of the target inventory service against open feign client failure timestamps. 3. Confirm whether premature timeout errors affect all feign client calls or specific inter-service routes. Phase 2. Investigation and evidence gathering. 1. Review open feign configuration properties in application.yml feign.client.config.default.connect timeout and feign.client.config.default.read timeout. 2. Compare feign configuration settings against Resilience 4J time limiter and underlying HTTP client Apache or OK HTTP pool options. 3. Test direct endpoint latency from client pods using kubectl exec with curl. Phase 3. Root cause analysis. 1. Evidence collected. Logs showed feign throwing retrievable exception at 1000 milliseconds, while Resilience 4J circuit breaker remained closed with a 5000 milliseconds threshold. 2. Primary root cause. Open feign default timeout override. Open feign defaulted to its built-in 1-second read timeout request.options default 1000 milliseconds, overriding the longer timeout configured in the underlying HTTP client, and causing the request to fail before Resilience 4J time limiter or circuit breaker policies could take effect. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Configure explicit open feign timeouts in config map feign.client.config.default.read timeout equals 5000 and perform a rolling restart. 2. Permanent resolution. Align open feign, Resilience 4J time limiter, and underlying HTTP client connection and read timeouts across all feign client bean configurations. 3. Validation. Confirm retrievable exception errors cease. Inter-service inventory calls succeed up to 5 seconds and latencies normalize. Phase 5. Recurrence prevention. 1. Standardize central open feign client auto configurations with uniform timeout hierarchies across all microservice archetypes. 2. Add automated integration tests in CI and CD pipelines, validating feign client timeout behavior under simulated latency. 3. Configure APM alerts on feign client retrievable exception counts. Pro tip interview insight. Open feign has its own built-in request.options timeouts default 1-second connect, 1-second read that operate independently of Resilience 4J or underlying HTTP clients. Always explicitly configure feign.client.config.default.connect timeout and read timeout in application.yml to align all timeout layers.
Follow up when expected. A logical continuation of the incident. How do open feign timeouts interact with Resilience 4J time limiter and circuit breaker layers during a slow downstream call?
Answer: open feign, Resilience 4J time limiter, and circuit breaker operate as nested layers. Whichever timeout threshold is shortest triggers first. If open feign's read timeout is set shorter than Resilience 4J's time limiter, feign throws retrievable exception before Resilience 4J can record a timeout or execute fallback logic.
Follow up 2 deeper. Experienced tester. How do you configure per client custom timeouts for specific open feign interfaces in Spring Cloud Open Feign?
Answer: in application.yml, specify individual feign client names under feign.client.config.clientName.read timeout equals 8000. In Java configuration, declare a custom at bean returning request.options with connect timeout. Read timeout scope to that specific feign client interface.
Follow up 3 curveball. What if an open feign client executes a post request that times out, and open feign's built-in retrier automatically retries the post request, causing a duplicate payment charge downstream?
Answer: by default, open feign's retrier retries failed requests. Automatic retries on non-idempotent post requests are dangerous. To fix, disable feign retries by declaring retrier.never_retry as a bean, or mandate idempotency key on all downstream endpoints.
Production Incident 92. An API gateway microservice routing thousands of concurrent REST calls stalls. Outgoing inter-service calls fail with org.apache.http.con.connection pool timeout exception. Timeout waiting for connection from pool, while destination microservices show zero load. As the on-call Java application support engineer, how do you resolve this connection pool exhaustion?
Answer: when an outgoing REST client connection pool exhausts due to default route limits, my priority is to inspect connection manager capacity, expand per route connection limits, and configure idle connection eviction using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check gateway error logs using kubectl logs for connection pool timeout exception or least timeout exception. 2. Inspect Grafana outgoing HTTP client metrics to verify active connection pool leasing and queue wait times. 3. Confirm destination microservice pod health to verify that downstream services are running normally with low CPU. Phase 2. Investigation and evidence gathering. 1. Review Apache HTTP client pooling HTTP client connection manager bean configuration in Spring context. 2. Check values configured for default max per route and max total properties. 3. Verify whether worker threads borrowing connections from the pool fail to close HTTP response entities or input streams. Phase 3. Root cause analysis. 1. Evidence collected. Gateway metrics showed default max per route capped at 2 active connections for the inventory service, while 150 worker threads queued for connections. 2. Primary root cause. Per route connection pool starvation. Apache HTTP client used default settings default max per route equals 2, max total equals 20, restricting concurrent connections to any single downstream host to only 2 connections and bottlenecking under load. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Expand Apache HTTP client connection pool parameters default max per route equals 200, max total equals 1000 via config map update and perform a rolling restart. 2. Permanent resolution. Configure explicit pooling HTTP client connection manager beans with background idle connection eviction tasks, evict idle connections. 3. Validation. Confirm connection pool timeout exception errors drop to 0, outgoing REST request latencies drop to 10 milliseconds and gateway throughput scales. Phase 5. Recurrence prevention. 1. Standardize high concurrency connection pool configurations across all microservice REST client archetypes. 2. Enable background connection eviction threads, evict idle connections with 5 time unit seconds on all Apache HTTP client beans. 3. Set Prometheus alerts for REST client connection pool utilization exceeding 80% of max total. Pro tip interview insight. Apache HTTP client defaults default max per route to only 2 connections per destination host. In high concurrency microservice architectures, an unconfigured REST client connection pool will bottleneck at 2 concurrent requests per target service. Always increase max con per route, for example 200, and max con total, for example 1000.
Follow-up when expected. A logical continuation of the incident. What is the precise architectural difference between default max per route and max total in Apache pooling HTTP client connection manager?
Answer. Max total sets the absolute maximum number of active HTTP connections allowed across all destination hosts combined. Default max per route sets the maximum number of concurrent HTTP connections allowed to any single individual target, host IP, or domain name.
Follow-up 2 deeper. Experience tester. Why must REST client connection pools periodically execute an idle connection eviction, task close idle connections, or close expired connections?
Answer. Downstream servers or firewalls silently close idle TCP connections after an idle timeout. If the client connection pool holds a closed connection without evicting it, the next outgoing HTTP request assigned to that stale connection, fails with no HTTP response exception. Idle eviction tasks purge stale sockets proactively.
Follow up 3 curveball. What if a downstream microservice drops an idle TCP connection without sending a FIN packet, and the client connection pool hands that stale connection to an active HTTP request thread?
Answer: the client thread sends the request over the dead socket and receives a TCP/RST or IO error. To prevent this, enable stale connection check or validate after inactivity with 2000 milliseconds on Apache HTTP client, forcing the pool to validate connection health before leasing it to an active request thread.
Production Incident 93. Following an API gateway upgrade, mobile app users experience immediate crash loops. Mobile client requests return HTTP 400 bad request or HTTP message, not readable exception, because the new backend deployment removed deprecated fields and renamed required request payload. Attributes. As the on-call Java application support engineer, how do you resolve this API version mismatch?
Answer: when an unversioned API release breaks legacy mobile clients due to payload schema changes, my priority is to restore backward-compatible endpoints, implement explicit URI or header versioning, and deploy payload transformers using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check API gateway HTTP response metrics for sudden spikes in 400 bad request and 422 unprocessable entity errors. 2. Verify mobile app crash logs to confirm deserialization failures on modified payload attributes. 3. Confirm whether payload schema breaking changes impact all client versions or specific mobile releases. Phase 2. Investigation and evidence gathering. 1. Inspect backend application logs using kubectl logs for HTTP message not readable exception or missing property errors. 2. Review open API or Swagger diffs between the previous release and current build for renamed or deleted JSON fields. 3. Check whether API gateway routing rules enforce explicit versioning such as /API/v1/orders versus /API/v2/orders. Phase 3. Root cause analysis. 1. Evidence collected. Gateway logs showed mobile app version 1.4 sending customer_address while backend expected shipping address. 2. Primary root cause. Non-version breaking release. A backend update renamed required JSON request fields on an unversioned endpoint /API/orders without maintaining backward compatibility for legacy mobile clients. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Deploy an API gateway payload transformation filter mapping customer_address to shipping address or enable the v1 backward compatible endpoint and perform a rolling restart. 2. Permanent resolution. Implement explicit URI path versioning /API/v1/orders and /API/v2/orders and enforce strict deprecation lifecycles. 3. Validation. Confirm mobile app v1.4 client checkout requests succeed, 400 bad request errors drop to 0%, and v2 endpoints process fresh payloads. Phase 5. Recurrence prevention. 1. Enforce consumer-driven contract testing using Pact or Spring Cloud Contract in CI and CD pipelines to block breaking API schema changes. 2. Mandate open API schema diff validation checks during build phases. 3. Enforce a minimum 6-month deprecation lifecycle policy for legacy API versions before decommissioning. Pro tip interview insight. Never publish breaking payload or schema changes on an existing API version. Mobile and third-party clients cannot be updated instantly. Always use URI path versioning /v1/ leads to /v2/ or header versioning, maintaining deprecated v1 endpoints until client traffic metrics show complete migration to v2.
Follow up when expected. A logical continuation of the incident. What are the advantages and trade-offs of URI path versioning /v1/ orders versus header or media type versioning except application/vnd.company.v1 plus JSON.
Answer: URI path versioning is highly visible, easy to test in browsers, and simple to route at API gateways, but pollutes URI namespaces. Header or media type versioning keeps URIs clean and follows REST purist principles, but makes client request caching and gateway path routing significantly more complex.
Follow up 2 deeper. Experience tester. How do consumer-driven contract tests packed or Spring Cloud Contract prevent breaking API changes from passing CI and CD deployment pipelines?
Answer: consumer-driven contract tests allow downstream clients to define expected JSON request or response contracts as test specifications. During upstream producer builds, contract testing plugins automatically execute tests against those specifications, breaking the CI and CD build if an upstream developer removes a field expected by a consumer.
Follow up 3 curveball. How do you gracefully deprecate an old API version using the HTTP sunset header RFC 8594 and API gateway traffic metrics?
Answer: when deprecating an endpoint, return the sunset HTTP header containing the exact retirement timestamp. For example, sunset Wednesday, November 11, 2026, 00:00:00 GMT. Monitor API gateway access logs for traffic hitting the sunset route, contacting remaining clients before turning off the route permanently.
Production Incident 94. During a mobile network connection blip, a user taps Pay Now on a $500 checkout. The first HTTP post request reaches the payment service and charges the card, but the network drops the response. The mobile app automatically retries the post request, resulting in a duplicate $500 charge on the customer's account. As the on-call Java application support engineer, how do you resolve this idempotency failure?
Answer: when network retries of non-idempotent HTTP post requests cause duplicate customer charges, my priority is to issue immediate customer refunds, implement idempotency key tracking in Redis, and enforce database unique constraints using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Check database payment transaction logs for duplicate order IDs and identical charge amounts submitted within seconds. 2. Inspect customer support ticket volumes to determine the total number of affected duplicate transaction accounts. 3. Immediately issue administrative refunds for verified duplicate payment charges via automated payment CLI scripts. Phase 2. Investigation and evidence gathering. 1. Review payment controller post endpoints for missing idempotency key HTTP header evaluation filters. 2. Check database schema definitions on the payments table for missing unique constraints on transaction idempotency keys. 3. Inspect Redis distributed lock and idempotency caching configurations. Phase 3. Root cause analysis. 1. Evidence collected. Payment logs showed 2 separate charge transactions executed 800 milliseconds apart carrying the exact same request body but lacking an idempotency key header. 2. Primary root cause. Missing idempotency key validation. The payment post endpoint executed payment charges directly without validating or caching an idempotency key header, allowing client network retries to process as independent new financial charges. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Deploy an emergency Spring web filter that intercepts incoming idempotency key headers and checks Redis for cached transaction responses before executing payments. 2. Permanent resolution. Implement a robust idempotency framework. Using Redis atomic locks, set key value NXEX 86400 and enforce SQL unique constraints on idempotency_key in the payments database table. 3. Validation. Simulate client network retries sending duplicate idempotency key headers, confirming 0% duplicate charges and verifying cached HTTP 200 OK responses. Phase 5. Recurrence prevention. 1. Mandate mandatory idempotency key HTTP header handling across all payment, order, and financial post or put-in points. 2. Enforce database unique constraints on idempotency keys across all transactional tables. 3. Implement automated network disconnect and retry testing in staging prior to production releases. Pro tip interview insight. HTTP post requests are non-idempotent by default. Network retries can cause duplicate payment charges. Always mandate an idempotency key HTTP header on financial endpoints, storing the key in Redis with a short lock or result cache, so duplicate requests return the cached original response without re-executing the transaction.
Follow up when expected. A logical continuation of the incident. How does an idempotency filter, using Redis set key value NXEX process, an incoming idempotency key header to prevent duplicate execution?
Answer. When an HTTP post request arrives, the filter executes an atomic Redis set key value NXEX 86400. If Redis creates the key successfully, the request proceeds and its response is cached. If the key already exists, the request is recognized as a duplicate, and the previously cached response is returned instead of executing the payment again.
Follow up 2 deeper. Experienced tester. What is the difference between idempotent HTTP methods get, put, delete, and non-idempotent HTTP methods post according to RFC 7231?
Answer. According to RFC 7231, idempotent methods get, put, delete can be called multiple times with the same parameters and produce the exact same side effects on the server state. Non-idempotent methods post create new server state on every invocation, requiring application-level idempotency key tracking to prevent duplicate processing.
Follow up 3 curveball. What if 2 identical concurrent requests carrying the same idempotency key reach 2 different microservice pod replicas at the exact same millisecond?
Answer. Because both requests arrive simultaneously, local in-memory checks fail. However, atomic Redis set NX, or a database unique constraint on the idempotency_key column, guarantees that only one pod successfully acquires the lock or inserts the row, while the second pod receives a duplicate key constraint violation and waits for the cached response.
Category 6 conclusion.
Mastering distributed communication, service discovery, and payload serialization is what protects modern microservices from cascading downstream latency, retry storms, and schema-breaking changes. By applying resilience 4J circuit breakers and bulkheads, enforcing lenient Jackson deserialization, standardizing ISO 8601 UTC timestamps, and tracking idempotency keys, you build an ultra-resilient, fault-tolerant REST architecture.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass. You send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Transition from Category 6 REST APIs, Microservices, and Serialization to Category 7 Reactive Programming.
Up until this point, we have solved incidents in traditional blocking thread per request architectures like Spring MVC and Tomcat. However, high-throughput systems are rapidly migrating to non-blocking, asynchronous event loop architectures, using Spring WebFlux and Project Reactor. Troubleshooting reactive systems requires an entirely different set of rules. As traditional stack traces break and thread locals disappear, we now transition to the final and most advanced application layer of Part 1, Category 7, Reactive Programming Spring WebFlux.
Category 7 Reactive Programming Spring WebFlux.
Reactive programming scenarios govern how neti event loops, non-blocking asynchronous pipelines, and backpressure mechanisms behave under massive concurrency. This reference grade category deep dives into resolving catastrophic event loop blocking, deciphering fragmented reactive thread dumps, managing fast producer backpressure memory leaks, tracing lost reactor contexts, preventing event loop CPU starvation, and debugging infinite zip hang states. Mastering these scenarios elevates you to the elite tier of modern Java application support.
Category 7 Reactive Programming Spring WebFlux 95 to 100.
Here are the 6 elite reactive programming incidents we will solve in this final category of Part 1. Incident 95. Blocking code on event loop freezes the entire WebFlux application. Incident 96. Reactive thread dump analysis fails due to asynchronous assembly boundaries. Incident 97. Backpressure failures exhaust heap memory during high-speed data streaming. Incident 98. Reactor context lost across threads breaks distributed APM tracing. Incident 99. Natty event loop starvation caused by heavy CPU-bound computations. Incident 100. Mono or flux never completing causes indefinite pipeline execution hangs. Total 6. Advanced reactive incidents. Let's dive into Incident 95 and conclude Part 1.
Production Incident 95. A high-throughput Spring WebFlux microservice completely freezes in production. API response times skyrocket to HTTP 504 gateway timeouts, yet container CPU utilization is near zero. As the on-call Java application support engineer, how do you resolve this reactive event loop blocking outage?
Answer. When a reactive application freezes with low CPU utilization, my priority is to identify blocking I/O calls hijacking the Natty event loop, deploy block hound for automated detection, and offload blocking tasks using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM metrics to confirm HTTP 504 gateway timeouts correlating with low CPU and flat JVM heap utilization. 2. Check container thread pools to verify if the limited number of reactor-http-n I/O worker threads are unresponsive. 3. Confirm whether the freeze affects all API endpoints or specific reactive data retrieval pipelines. Phase 2. Investigation and evidence gathering. 1. Generate a JVM thread dump using jcmd1 thread.print. 2. Analyze stack traces for Natty event loop threads reactor-http-n IO-star stuck in waiting or runnable states on blocking socket reads. 3. Inspect source code for imperative blocking API such as REST template, java.lang.thread.sleep, or standard JDBC queries executing inside mono.map or flux.flatmap. Phase 3. Root cause analysis. 1. Evidence collected. Thread dump showed all 4 reactor-http-n IO event loop threads blocked inside socket input stream.socket read 0 executing a traditional JDBC result set extraction. 2. Primary root cause. Event loop thread hijacking. A developer executed a synchronous, blocking JDBC database query directly inside a reactive flux.map operator. Because Natty typically provisions a small number of event loop threads by default, approximately equal to the available CPU cores. Blocking just 4 threads paralyzed the entire microservice, preventing it from processing any other concurrent network requests. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Perform a rolling restart to free the stuck Natty event loops and restore API traffic. 2. Permanent resolution. Offload the legacy blocking JDBC query to a dedicated bounded thread pool using .subscribe on with schedulers .bounded elastic, or migrate the data access layer to Spring Data R2DBC using a non-blocking R2DBC driver. 3. Validation. Confirm reactor-http-n IO threads remain free in thread dumps. CPU scales normally under load and HTTP 504 errors drop to 0. Phase 5. Recurrence prevention. 1. Integrate block hound.install in non-production environments to automatically detect and throw errors when blocking calls execute on the event loop. 2. Prohibit the use of blocking libraries REST template, Feign, JDBC and WebFlux repositories, mandating web client and R2DBC. 3. Enforce architecture reviews for all reactive pipeline integrations. Pro tip interview insight. Spring WebFlux uses a tiny pool of Natty event loop threads, usually 1 per CPU core. If you execute a single blocking call like JDBC, REST template, or thread.sleep on the event loop, that thread cannot accept new connections. Blocking just 4 event loop threads freezes the entire application instantly. Always offload blocking legacy code using subscribe on with schedulers .bounded elastic.
Follow up when expected. A logical continuation of the incident. How does schedulers .bounded elastic safely isolate blocking I/O calls without crashing a reactive application?
Answer. Schedulers.bounded elastic provides a dynamically growing thread pool, specifically designed for legacy blocking I/O. By wrapping the blocking call in mono dot from callable and chaining dot subscribe on, with schedulers dot bounded elastic, the blocking execution is pushed off the natty event loop onto a dedicated background thread, keeping the event loop free to handle concurrent network traffic.
Follow up 2 deeper. Experienced tester. What is Blockhound, and how does it detect hidden blocking calls inside third-party libraries during testing?
Answer: Blockhound is a Java agent developed by Project Reactor. It instruments the JVM and intercepts known blocking methods like socket reads or file I/O. If a thread marked as a non-blocking event loop attempts to execute these methods, Blockhound immediately throws a blocking operation error, exposing hidden blocking code before it reaches production.
Follow up 3 curveball. What is the precise execution difference between publish on and subscribe on in a Reactor pipeline?
Answer: Subscribe on dictates the thread context for the source emission, the beginning of the pipeline, and affects the entire chain upwards. Publish on shifts the execution context for all subsequent operators downwards in the chain. Use subscribe on to offload a blocking database read, and publish on to offload heavy CPU parsing after the read completes.
Production Incident 96. A WebFlux microservice experiences a silent transaction stall. An engineer generates a JVM thread dump, but the stack traces show generic Reactor internal methods like fluxmap fusible.subscribe and eventloop.run, completely hiding the actual application business logic that is failing. As the on-call Java application support engineer, how do you debug this fragmented reactive stack trace?
Answer: When traditional thread dumps fail to reveal business logic in reactive pipelines, my priority is to bridge the gap between assembly and execution phases, enable Reactor debugging hooks, and trace the asynchronous flow using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Confirm that traditional APM and thread dumps lack actionable stack frames, showing only netty event loop boilerplate. 2. Check application error logs for generic on error not implemented exception or dropped reactive signals. 3. Verify whether the transaction stall is localized to specific data streaming pipelines or affecting the entire application. Phase 2. Investigation and evidence gathering. 1. Enable Project Reactor's debug agent in a staging or isolated production canary using hooks dot on operator debug. 2. Inspect the enriched exception stack trace, which now includes the assembly trace where the pipeline was declared. 3. Review source code for complex nested flat map operators lacking dot checkpoint with description markers. Phase 3. Root cause analysis. 1. Evidence collected. An enriched assembly trace revealed the exception originated during the instantiation of a web client call inside order service.enrich order. 2. Primary root cause. Asynchronous stack fragmentation. In reactive programming, the thread that declares the pipeline assembly time is almost never the thread that executes the pipeline execution time. When a failure occurs during execution, the JVM stack trace only shows the execution thread, completely losing the context of where the pipeline was originally constructed in the business logic. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Insert explicit dot checkpoint with order enrichment step markers in the failing reactive chain and deploy a hotfix to expose the exact failure point in logs. 2. Permanent resolution. Integrate Reactor debug agent .init or micrometer context propagation to capture low overhead assembly stack traces globally. 3. Validation. Trigger the failure scenario. Confirm the logs now print a clear assembly trace pointing to the exact class and line number and deploy the functional fix. Phase 5. Recurrence prevention. 1. Mandate the use of Reactor debug agent .init in early application boot phases to retain stack visibility without extreme overhead. 2. Enforce developer guidelines requiring dot checkpoint markers on critical or highly complex reactive pipelines. 3. Integrate micrometer tracing to correlate fragmented reactive logs across distributed infrastructure boundaries. Pro tip: interview insight. Traditional Java thread dumps are practically useless in Spring WebFlux because pipelines are declared on one thread and executed on another asynchronously. An exception thrown during execution has no stack frames pointing back to your controller. Always initialize reactor debug agent .init to stitch assembly, and execution traces back together.
Follow up when expected. A logical continuation of the incident. What is the performance impact of enabling hooks on operator debug in a live production environment?
Answer: hooks on operator debug captures a heavy thread stack trace upon the creation of every single reactive operator in the application. This incurs massive CPU and memory allocation overhead, severely degrading production performance. It should only be used locally. In production, reactor debug agent .init is preferred because it rewrites bytecode at class loading time, capturing traces with near zero overhead.
Follow up 2 deeper. Experience tester. How does the checkpoint operator provide targeted debugging without global performance overhead?
Answer: checkpoint with description captures the assembly trace only at the exact point it is inserted into the flux or mono chain. If an error propagates through that checkpoint, the exception is enriched with the provided description. This allows developers to instrument critical, failure-prone pipelines with zero global performance penalty.
Follow up 3 curveball. What if a reactive stream throws an exception, but it is silently swallowed and nothing appears in the application logs?
Answer: this happens when an exception occurs inside a reactive chain, but the subscriber does not implement an error handler in its .subscribe call. The reactive stream routes the exception to a generic hooks on error dropped, which may not log properly. Always handle errors explicitly using .do on error, .on error resume, or by providing an error consumer in .subscribe.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 97. A WebFlux service consumes high-speed streaming data from a Kafka topic and writes it to a slow legacy database. During a traffic burst, the application crashes with out-of-memory error and reactor.core.exceptions $overflow exception. As the on-call Java application support engineer, how do you resolve this backpressure failure?
Answer: when a fast producer overwhelms a slow consumer triggering or overflow exception, my priority is to analyze heap retention, enforce backpressure dropping or buffering strategies, and rate limit the stream using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect Grafana JVM heap metrics to confirm rapid heap exhaustion immediately following the Kafka traffic burst. 2. Check application error logs for exceptions $overflow exception, indicating a reactive queue breach. 3. Confirm whether the legacy database downstream is exhibiting latency, creating a fast producer or slow consumer mismatch. Phase 2. Investigation and evidence gathering. 1. Capture a JVM heap dump and inspect. Eclipse MAT for massive accumulations of queues or flux buffer internal arrays holding unprocessed message payloads. 2. Review the reactive Kafka receiver code for unbounded buffer or missing backpressure operators. 3. Inspect the R2DBC database writer pipeline for slow execution times restricting consumer throughput. Phase 3. Root cause analysis. 1. Evidence collected. Heap dump showed 2 GB of memory retained by an unbounded internal reactor queue holding pending Kafka payloads. 2. Primary root cause. Missing backpressure strategy. The Kafka producer emitted 10,000 events per second, but the legacy database could only process 500 per second. Lacking an explicit backpressure strategy, the reactive framework buffered the excess 9,500 messages per second in memory indefinitely, ultimately causing heap exhaustion and an overflow exception. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Restart the crashed pods, temporarily pause the Kafka consumer to allow the database to recover, and apply an emergency on backpressure drop operator to protect heap memory. 2. Permanent resolution. Implement limit rate with 256 to control Kafka pre-fetch requests, and apply on backpressure buffer with max size, overflow handler, buffer overflow strategy, drop _oldest with a bounded maximum size, and an explicit overflow strategy. 3. Validation. Resume Kafka consumption, confirm JVM heap memory remains flat below 60%, and verify stable database ingestion. Phase 5. Recurrence Prevention. 1. Mandate explicit backpressure strategies on backpressure buffer, on backpressure drop, or limit rate on all streaming asynchronous data pipelines. 2. Monitor Kafka consumer lag metrics in Grafana to detect fast producer or slow consumer mismatches early. 3. Upgrade legacy database drivers to fully reactive, non-blocking R2DBC drivers to improve consumer throughput. Pro tip interview insight. Backpressure is the core mechanism of reactive streams. It allows a slow subscriber to signal a fast publisher to slow down data emission. If the publisher ignores this, or if the stream originates from an unbounded source, you must explicitly define how to handle the excess data using dot on backpressure drop, or a bounded dot on backpressure buffer to prevent
Follow up when expected. A logical continuation of the incident. How does the dot limit rate with N operator implement backpressure mathematically between a publisher and a subscriber?
Answer: dot limit rate with 100 splits downstream, demand requests into smaller batches. The subscriber initially requests 100 items from the publisher. When 75% of those items, 75 items are successfully processed, it requests another 75 items, ensuring the publisher never overwhelms the subscriber's internal processing buffers.
Follow up 2 deeper. Experienced tester. If you apply dot on backpressure drop, what happens to the data, and how do you ensure critical business events are not permanently lost?
Answer: dot on backpressure drop discards excess emitted items when the downstream subscriber cannot keep up. To prevent silent data loss, you must provide a consumer hook, for example, dot on backpressure drop with item to dead letter service, dot save with item to capture the discarded elements, and persist them to a dead letter queue or external log for later reprocessing.
Follow up 3 curveball. How does reactive backpressure differ from traditional TCP flow control?
Answer: TCP flow control operates at the OS network layer. If a receiver's TCP window fills up, it stops acknowledging packets, forcing the sender OS to slow down. Reactive backpressure operates at the application software layer, allowing explicit programmatic rules like buffering, dropping, or throwing exceptions when application logic cannot process the incoming payloads fast enough.
Production Incident 98. An API gateway routing requests to a WebFlux service drops all distributed tracing IDs midway through request processing. Consequently, downstream calls lack tracking headers, breaking APM visibility, and failing security token validation. As the on-call Java application support engineer, how do you resolve this lost reactive context?
Answer: when thread locals fail across asynchronous boundaries, causing APM trace and security context loss, my priority is to inspect context propagation pipelines, inject reactor context view, and enforce micrometer context propagation using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM distributed tracing dashboards Jaeger or Datadog to verify where the trace continuity breaks orphan spans. 2. Check downstream microservice error logs for 401, unauthorized caused by missing propagated JWT security tokens. 3. Confirm whether the context loss impacts all reactive pipelines or only specific asynchronous boundaries. Phase 2. Investigation and evidence gathering. 1. Review Spring WebFlux controller code for legacy thread local usage to store user authentication or trace IDs. 2. Inspect reactive pipelines for asynchronous boundaries like publish on, subscribe on, or flat map that switch underlying execution threads. 3. Verify whether micrometer context propagation libraries are included in the pom.xml. Phase 3. Root cause analysis. 1. Evidence collected. Security tokens stored in standard thread local variables returned null after a .publish on with scheduler's .parallel operator in the mono chain. 2. Primary root cause. Thread local context loss. Thread local variables belong to a single OS thread. When the reactive pipeline crossed an asynchronous boundary via publish on, execution moved to a different thread, leaving the thread local security context behind, and causing downstream calls to fail authentication. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Revert the asynchronous publish on operator temporarily if blocking is not an immediate risk, restoring single-thread execution and unblocking critical traffic. 2. Permanent resolution. Replace legacy thread local usage with Reactor's context, AP. Writing via context, write and reading via mono.defer contextual, and integrate micrometer context propagation to automatically bridge remaining thread locals. 3. Validation. Trigger requests, confirm downstream APM traces are fully linked, and verify HTTP 200 OK responses on secured downstream APIs. Phase 5. Recurrence prevention. 1. Ban explicit thread local variable declarations in all WebFlux and Reactive codebases via SonarQube rules. 2. Standardize micrometer tracing for all Spring Boot 3 Reactive microservices to automate MDC and trace ID propagation. 3. Conduct API end-to-end tracing tests to explicitly validate distributed context flow. Pro tip: interview insight. The most common mistake engineers make when migrating from Spring MVC to Spring WebFlux is assuming thread local variables used for security tracing and MDC will survive. They do not. Reactive pipelines switch threads constantly. Always use Reactor's context API or micrometer context propagation to pass states safely across Reactive streams.
Follow-up 1 expected. A logical continuation of the incident. How does Reactor's context differ fundamentally from a traditional thread local map?
Answer: a thread local is bound to a specific physical OS thread. Reactor's context is bound to a specific subscription lifecycle in the Reactive pipeline. The context flows immutably upstream from the subscriber to the publisher, passing data safely across any thread boundary without risk of data bleeding.
Follow-up 2 deeper. Experience tester. How do you use mono.defer contextual to extract a security token from the Reactor context and apply it to an outgoing web client request?
Answer: wrap the web client execution in mono.defer contextual with CTX to block. Inside the Lambda, extract the security token using CTX.get with authorization and append it to the outgoing HTTP call via .header with authorization, token. This ensures the request executes with the correct user context regardless of the active execution thread.
Follow-up 3 curveball. Will Java 21 scoped values eventually replace the need for Reactor context in Spring WebFlux applications?
Answer: yes. Scoped values are designed as a lightweight, thread-safe replacement for thread locals. Emerging Java platform features, such as scoped values, may reduce some thread local use cases in the future, but Reactor context remains the standard context propagation mechanism for Spring WebFlux today.
Production Incident 99. An encryption microservice running Spring WebFlux accepts incoming client connections cleanly, but API response latencies fluctuate wildly between 10 milliseconds and 6 seconds. CPU utilization is moderately high. Thread dumps show no blocking I/O, but event loop threads are fully saturated. As the on-call Java application support engineer, how do you resolve this CPU starvation?
Answer: when heavy computations starve nutty event loops causing erratic latency, my priority is to profile CPU execution hotspots, offload CPU-bound logic to parallel schedulers, and restore event loop capacity using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM latency metrics to confirm erratic latency spikes without matching downstream I/O latency. 2. Check container CPU utilization in Grafana to verify if the application is experiencing high CPU consumption. 3. Confirm whether the erratic latency impacts all incoming WebFlux endpoints, or specifically the encryption API routes. Phase 2. Investigation and evidence gathering. 1. Execute a sync profiler as prof-ecpu to generate a CPU flame graph of active processing threads. 2. Analyze the flame graph to verify if nutty event loop threads Reactor-http-n IO-* are executing heavy computational methods like JSON serialization or cryptography. 3. Review reactive pipeline code for missing .publish on scheduler isolation boundaries. Phase 3. Root cause analysis. 1. Evidence collected. CPU flamegraph showed reactor-http-n IO threads spending 90% of their execution time inside bouncy castle crypto.encrypt. 2. Primary root cause. Event loop CPU starvation. A developer executed a highly CPU-intensive payload encryption algorithm directly on the natty event loop. Because event loops are few in number, holding them hostage for heavy math prevented them from acknowledging new network requests or executing other fast non-blocking pipelines. Phase 4. Resolution and service restoration. 1. Immediate recovery. Reduce MTTR. Temporarily increase application replicas manually or via HPA to distribute incoming requests across more event loop instances while the application fix is prepared. 2. Permanent resolution. Inject .publish on with schedulers .parallel immediately before the encryption operator in the mono chain to offload the heavy math execution to a dedicated CPU-bound background thread pool. 3. Validation. Confirm CPU flamegraphs show reactor-http-n IO threads clear of encryption processing, and verify API latency flattens to a stable 15 milliseconds. Phase 5. Recurrence prevention. 1. Mandate asynchronous offloading via schedulers .parallel for all heavy cryptographic, JSON serialization and image processing tasks. 2. Integrate block-hound with custom CPU time threshold triggers to flag computationally heavy methods running on event loops. 3. Conduct load testing with strict IP-IP99 latency SLAs to detect event loop starvation before deployment. Pro tip: interview insight. In Spring WebFlux, natty event loops can be parallelized by two things: blocking IO thread.sleep or JDBC, and heavy CPU-bound tasks like encryption or massive JSON parsing. Always offload heavy math or CPU operations to .publish on with schedulers .parallel to keep event loops free for high-speed network routing.
Follow up when expected. A logical continuation of the incident. What is the difference between schedulers .bounded elastic and schedulers .parallel when offloading tasks in Project Reactor?
Answer. Schedulers .bounded elastic creates a large, dynamically growing thread pool, specifically designed to safely absorb long-running blocking I/O tasks. Schedulers .parallel creates a small, fixed-size thread pool typically equal to CPU cores, specifically optimized for high-speed, non-blocking CPU-intensive math operations.
Follow up 2 deeper. Experienced tester. How does the netty event loop group architecture process incoming TCP connections and asynchronous callbacks?
Answer. Netty uses a boss event loop group to accept incoming TCP connections and hand them off to a worker event loop group. The worker threads multiplex thousands of active connections simultaneously via non-blocking EPOL/KQ selectors, processing incoming bytes and executing reactive callback closures.
Follow up 3 curveball. What if massive JSON parsing is starving the event loop on every incoming request before the application logic even executes? How do you offload Jackson parsing in WebFlux?
Answer. By default, Spring WebFlux executes Jackson JSON deserialization on the natty event loop as it reads the request body. If the JSON payloads are massive, this starves the loop. To fix, implement a custom HTTP message reader or manually parse raw data buffers after offloading the pipeline via .publish on with schedulers .parallel.
Production Incident 100. A reactive aggregation endpoint combines user profile data and billing status using mono.zip. Sporadically, the endpoint hangs completely, leaving HTTP requests open until API gateways forcefully terminate them with HTTP 504 gateway timeout. As the on-call Java application support engineer, how do you resolve this infinite zip hang state?
Answer. When a reactive aggregation pipeline hangs indefinitely awaiting completion signals, my priority is to inspect publisher lifecycles, apply explicit timeouts, and handle empty signals safely using a structured 5-phase response plan like below. Phase 1. Initial assessment scope and impact. 1. Inspect APM latency charts to verify whether requests are failing fast or hanging open until maximum upstream HTTP timeouts trigger, for example, 30 seconds. 2. Check thread dumps using kubectl exec to confirm worker threads are not blocked, indicating a logical reactive stream pause rather than thread starvation. 3. Isolate the specific aggregation API endpoint utilizing zip, or combine latest operators. Phase 2. Investigation and evidence gathering. 1. Inject .log operators into the reactive chain to trace on next, on complete, and on error signals for both the profile and billing publishers. 2. Verify whether downstream web client calls are returning HTTP 404 not found, mapping to empty reactive publishers. 3. Check the mono.zip or flux.zip combinations for missing fallback logic like switch if empty or default if empty. Phase 3. Root cause analysis. 1. Evidence collected. Reactive.log traces showed the billing status mono executing on complete immediately without emitting an on next item empty completion. 2. Primary root cause. Reactive aggregation stall. The billing publisher never produced the required value for the aggregation because the pipeline lacked timeout and fallback handling. The combined mono.zip operation could not produce the expected aggregate response, leaving upstream requests open until the gateway timeout expired. Phase 4. Resolution and service restoration. 1. Immediate recovery reduce MTTR. Deploy a hotfix applying .timeout with duration of seconds with 5 to the combined mono pipeline, forcing hanging requests to fail fast and releasing upstream resources. 2. Permanent resolution. Append .default if empty with default billing .null to the billing mono publisher before it enters the zip operator, guaranteeing that the billing publisher emits a fallback value, allowing mono.zip to construct the combined result. 3. Validation. Confirm API gateway 504 timeouts drop to 0, verify the endpoint successfully aggregates partial data, and monitor execution times. Phase 5. Recurrence prevention. 1. Enforce mandatory .timeout operators globally on all outgoing web client requests and top-level REST controller returns. 2. Mandate fallback values default if empty or switch if empty on all publishers participating in zip or combine aggregations. 3. Implement comprehensive unit tests, explicitly injecting mono.empty to validate pipeline resilience against missing data. Pro tip interview insight. Mono.zip requires exactly one emitted item from every publisher to proceed. If any publisher completes empty, the aggregation cannot produce the expected combined result. Always provide explicit fallback values default if empty or timeout handling before combining publishers.
Follow up when expected. A logical continuation of the incident. What is the precise operational difference between mono.empty and mono.just with null?
Answer. Mono.just with null is an illegal operation in Project Reactor and immediately throws a null pointer exception, because reactive streams forbid null emissions. Mono.empty represents a successful completion signal on complete without emitting any data item, which is fully valid but alters the behavior of aggregators like zip.
Follow up 2 deeper. Experience tester. How does the .timeout operator behave when applied to a reactive stream, and what exception does it trigger?
Answer. The .timeout with duration operator starts a background timer. If the publisher does not emit a subsequent item or completion signal within the duration, the operator cancels the upstream subscription and throws a java.util.concurrent.timeout exception downstream, unblocking the pipeline.
Follow up 3 curveball. What if a reactive web client call successfully receives data, but the processing inside a subsequent flat map operator enters an infinite computational loop? Will Blockhound detect it?
Answer. No. Blockhound detects blocking API calls like thread.sleep or socket.io. An infinite computational loop like an endless while loop is CPU-bound execution, not a blocking system call. Blockhound ignores it, but the loop will starve the neti event loop, requiring thread dumps or CPU profiling to diagnose.
Category 7 Conclusion. Mastering reactive architecture.
Troubleshooting non-blocking architectures requires an elite understanding of event loop mechanics, backpressure, and asynchronous context propagation. By deploying Blockhound, offloading blocking I/O to bounded elastic schedulers, enforcing explicit timeouts, and capturing assembly traces, you have mastered the most complex application layer in modern Java. Spring WebFlux and Project Reactive.
Part 2 Conclusion. 49 Production Incidents Mastered.
Congratulations on completing Part 2. We have conquered 49 complex production incidents spanning Spring Boot profile mismatches, HikariCP connection pool exhaustion, database deadlocks, downstream REST API cascades, and reactive WebFlux event loop freezes. You now possess a highly advanced blueprint for stabilizing the enterprise framework and data persistence layers.
Transition from Part 2 to Part 3 Cloud-Native Infrastructure.
While mastering the Spring Boot framework, database tuning, and reactive pipelines guarantees application-level stability, your microservices will still fail if the underlying platform collapses. What happens when the Linux host runs out of file descriptors? Kubernetes evicts your pods due to node pressure, or Kafka consumer lag spirals out of control. We must now transition our focus from inside the application to the massive infrastructure surrounding it. Part 3. Linux OS, Kubernetes, and Kafka event streaming.
Coming up in Part 3, Linux, Kubernetes, networking, and Kafka.
In Part 3, we tackle incidents 101 through 155, focusing entirely on cloud-native infrastructure, networking, and event streaming. Category 8. Linux OS, Infrastructure and Cloud Platform Bottlenecks 16 Incidents. Category 9. Kubernetes, Containers and Service Mesh Outages 15 Incidents. Category 10. Networking, TLS, Certificates and API Proxies 12 Incidents. Category 11. Messaging Pipelines, Kafka and RabbitMQ 12 Incidents. 55 Advanced Infrastructure and Messaging Incidents ahead in Part 3.
Continue your masterclass journey.
Congratulations on completing Part 2. You are now halfway through the Ultimate Production Support Masterclass. 1. Watch Part 3 immediately. Click the link in the description below to jump straight into Part 3 Incidents 101 to 155. 2. Bookmark the full series. Check the description for links to all 4 parts of this 195-incident masterclass. 3. Subscribe and share. Subscribe to the channel and share this masterclass with your engineering team to help elevate production engineering standards everywhere. Thank you for watching Part 2. Click the link in the description below and see you in Part 3.
Are you tired of generic interview prep? You can spend weeks studying generic interview questions, only to walk into a tech interview and realize they are asking about completely different tools and real-world scenarios. A tech title means nothing. A data engineer, DevOps engineer, or SAP consultant role is completely different at every single company. If you are not studying for the exact tech stack in the job description, you are wasting your time. That is exactly the problem we solve. Whether your upcoming interview is for SAP, DevOps, Salesforce, data engineering, cloud architecture, or cybersecurity, we will build a custom interview cheat sheet designed specifically for your target role. How we build your masterclass: you send us the exact job description. We analyze the technologies, the dependencies, and the seniority level. Then, we prepare a highly customized package with predicted interview rounds, realistic mock interview scripts, and targeted technical questions and answers. Stop guessing what managers will ask. If you have an upcoming interview and would like customized mock interview scripts and targeted practice questions and answers built specifically around your job description, feel free to email me at inquiry.aceinterviews@gmail.com. Please include these 4 details. 1. Your exact job description. 2. Your target role. 3. The interview date if known. 4. Your relevant experience level. Walk in with absolute confidence. I will personally review your submission and let you know what type of preparation package would provide the most value. We will analyze the requirements and build the exact custom mock scripts and questions and answers you need to get the offer. What if you people want a continuous study instead, with most commonly asked interview questions and answers PDFs? But what if you do not have an active interview lined up right now? If you want to proactively build your skills over time, we have recently launched our Master Vault subscription model. This is an all-access pass containing most commonly asked interview questions and answers PDFs of various tech roles in every single major technology like DevOps, SAP, testing, Salesforce, data engineering, cloud, Java and Python, etc. Choose the full bundle or specific paths, but we understand that unlocking every technology at once might feel overwhelming. If you are solely an SAP consultant, a Salesforce developer, or a DevOps engineer, you do not need the entire Master Vault. We redesigned the ecosystem so you can subscribe to the unrestricted full bundle or choose individual targeted vaults tailored specifically to your career. The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.